"23 million light-years away, the Whirlpool Galaxy spins like a flawless cosmic pinwheel, yet every turn drags gas, dust, and whole star systems toward a darker truth. Follow its glowing arms inward, and the beauty starts to feel like a warning. At the centre, do we find a nursery forging new suns, or a hungry black hole tearing them apart? A single galaxy can look like a masterpiece, until you measure the forces that keep it turning. In the Whirlpool Galaxy, beauty is only the visible skin of a relentless machine. What you're seeing is not a photograph of a place, it's a record of physics in motion written in light across deep time. Every bright knot and every dark lane marks a decision made by gravity, pressure, and angular momentum. In this documentary, we travel inward through the Whirlpool Galaxy, known as M51, following the structures that seem decorative until you read them as evidence. Spiral arms are not painted on a disk. They are patterns that move through it, gathering gas like a tide. Where that gas compresses, clouds cool and thicken, and the next generation of stars begins to assemble. But starbirth is never gentle, and it never happens in isolation. Radiation sculpts cavities, winds push back, supernovae arrive like punctuation, seeding space with heavier elements and stirring the interstellar medium into new shapes. The same processes that light the arms also limit them, turning abundance into scarcity and order into turbulence. To understand M51, we have to learn how astronomers see what eyes cannot. We'll shift through wavelengths, infrared to trace dust-warmed nurseries, radio to map hidden hydrogen and molecular gas, and X-rays to reveal hot plasma and extreme environments. Each band is a different witness, and together they testify to a galaxy that is alive, cycling matter, through phases we can measure even from millions of light-years away. As we move closer to the inner regions, the rules begin to feel stricter. Orbits tighten, speeds rise, and the spiral's graceful geometry becomes a map of constraints. Resonances, bottlenecks, and gravitational torques that can either trap gas in rings or send it farther down. In the centre, time itself seems to shorten, because the distances are smaller and the energies higher, and hovering over every step is the central question. Which physical processes, acting across scales from tens of thousands of light-years to the space between stars, shape a spiral galaxy's life and decide what it becomes? By tracing those processes in M51, we're also testing a mirror held up to our own Milky Way, because the forces that organise the whirlpool are the same forces that have governed our sky for billions of years. This is an exploratory descent through a system that builds stars, destroys them, and remembers them in its chemistry. It is a journey through dust that hides creation, through light that betrays motion, and through gravity that never stops negotiating. Follow the evidence inward, and the whirlpool will stop looking like a picture and start behaving like a story. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We begin with first light arriving from deep space, then ride the spiral blueprint into cold nebulae and evolving star populations. From there, we trace the hidden highways of gravity toward the nucleus, where the galaxy's final regulator waits in the dark. Space begins as distance without landmarks, and distance becomes time when light is our messenger. In the black between stars there is no ruler and no road, only angles, faint glows, and patient measurement. Ahead, in the direction of Cain's Venatici, a dim patch holds its shape against the dark. It is not a star, and it is not a cloud in our own sky. That patch is the Whirlpool Galaxy, M51, suspended about 23 million light-years away. The number is not a metaphor, and it is not a poetic exaggeration. It is a measure of how long its light has been travelling to reach us, uninterrupted except by the thin dust of intergalactic space. A light-year is distance, not duration, yet it is defined by motion through time. Light covers about 9.5 trillion kilometres in 1 year, and in vacuum it does not tire. Multiply that by 23 million, and the scale stops fitting intuition. Our minds were not built for numbers that large. Even the units feel strange, because they bind space and time together in one phrase. If a spacecraft could travel at the speed of light, it would still need 23 million years to arrive. At 1% of light speed, the trip becomes billions of years, longer than complex life has existed on Earth. That comparison is not just dramatic, it is diagnostic. Intergalactic travel quickly collides with biology, engineering, and the finite span of civilizations. Look-back time makes the distance stranger, because astronomy is always delayed. We do not see M51 as it is now, and we never can in the present tense. We see it as it was when Earth's early ancestors were already walking, but before modern humans existed. The photons reaching our detectors left M51 when mammoths still roamed and ice sheets still shaped continents. Some of that light began its journey before the first cave paintings, before agriculture, before recorded history. Every telescope is a time machine with a narrow window, and every observation is a delayed report. The universe does not send updates, it sends archives. That delay is not a flaw, and it is not a limitation we can engineer away. It is the only way astronomy works because information cannot travel faster than light. We cannot touch a galaxy, but we can read what its light carries, encoded in brightness, colour, and fine spectral lines. Brightness tells us energy output and distance when calibrated, although the calibration itself rests on careful ladders of measurement. Colour and spectrum tell us temperature, composition, and motion along our line of sight through Doppler shifts. The image is a map, and the spectrum is a set of fingerprints, and together they let us infer physics across impossible scales. It is a quiet miracle of method, refined over centuries from Galileo's first telescope to modern detectors that count individual photons. As we close in, the smudge resolves into a classic spiral, and the frame begins to fill with structure. Two main arms wind outward from a bright centre, with smaller feathers and spurs trailing behind like combed threads. The arms do not form a perfect circle, and the disc is not a smooth plate. It looks alive, patched, textured, and uneven, as if weather systems were frozen into starlight. This is a grand design spiral galaxy, one of the clearest examples in the nearby universe. Its arms are not solid structures, and they are not fixed rails that stars ride forever. They are patterns shaped by gravity and by the response of gas and stars moving through a rotating disk. To understand the pattern, it helps to imagine traffic on a circular highway. Cars move through a jam, but the jam can persist, and the location of congestion can drift. In galaxies, density waves act in a similar way. Regions of enhanced gravity gently crowd orbits and compress gas. Stars pass through the arms, while the arm pattern can remain coherent for long periods. The elegance we see is built from differential rotation, where inner regions orbit faster than outer ones. That shear stretches features, and gravity organizes them, and the result is a spiral that can endure. The arms glow because they host star formation, and star formation announces itself in color. Blue clusters mark short-lived massive stars that burn hot and die young, shining intensely for only a few million years. Pinkish nebulae trace ionized hydrogen around newborn stars, where ultraviolet light strips electrons from atoms and makes the gas fluoresce. Dark lanes cut across the bright disk, where dust blocks starlight and hides the youngest regions from optical view. In high-resolution images, those lanes look like rivers of soot, braided and broken, curving along the inner edges of the arms. The center shines more steadily, packed with older stars and deeper gravitational potential, and its light is warmer, more gold than blue. M51 is not alone, and its loneliness matters to its shape. A smaller companion galaxy, NGC 5195, hangs near one arm like a tug on a spinning wheel. Their interaction distorts orbits and compresses gas, and it can amplify spiral structure that might otherwise be weaker. Tidal forces pull streams of material and stir the disk, creating density waves that organize where clouds collapse. The whirlpool is beautiful, but the beauty is partly an after-effect of gravitational stress. In a sense, we are watching choreography written by gravity, with the companion acting as a persistent perturbation. This documentary follows a simple premise, and it is also a promise about scale. We will travel inward from the outskirts of M51 to its core, using the spiral arms as our corridor. The closer we get, the more extreme the environment becomes, and the more the galaxy resembles a machine under load. Densities rise, collisions become more frequent, and energy release becomes more violent. The central question is not only what M51 looks like, because appearance is only the surface. The question is what processes build that look, and what they imply about spiral galaxies like our own. To answer it, we need more than visible light. because the visible is biased toward what shines easily. Optical telescopes show the stars we can see directly, and they outline the galaxy's basic architecture in crisp detail. Yet much of a galaxy's mass and activity is hidden in gas, dust, and dark components that do not shine in the optical. Dust is especially deceptive because it both obscures and reveals, blocking starlight while re-radiating energy elsewhere. Multi-wavelength astronomy is not a luxury. It is how we avoid mistaking the visible surface for the whole system. Infrared light reveals what dust conceals, and it changes the mood of the galaxy. Dust grains absorb ultraviolet and optical photons, heat up, and re-radiate in the infrared, turning hidden nurseries into glowing knots. In M51, infrared maps highlight embedded star-forming regions still wrapped in their natal clouds. They show where energy is being processed by the interstellar medium rather than escaping directly. Infrared also traces cooler stars that dominate mass but not brightness in blue light, giving a steadier view of the underlying stellar population. When the image shifts to infrared, the arms look less like painted lines and more like warm currents. Radio observations reach even deeper into the cold, where star formation begins before it becomes luminous. At radio wavelengths, we detect atomic hydrogen through its 21-centimeter line, a transition so rare that it reveals vast reservoirs only because space is so large. We also map molecular gas through carbon monoxide as a proxy for hydrogen molecules, because cold H2 is difficult to detect directly. These gases are the raw material for future stars, and their distribution sets the galaxy's potential for renewal. Radio maps show the streaming motions along arms, the reservoirs that can be triggered by compression, and the holes carved by past activity. They also reveal magnetic fields through polarized emission, another invisible influence on gas flow that can guide charged particles and resist collapse. X-rays show the opposite extreme, where matter is stripped to plasma and heated to millions of degrees. They come from hot gas in shock waves, from compact remnants, and from the aftermath of stellar death. Supernova explosions carve bubbles and accelerate particles, and their debris glows in X-rays as it expands into surrounding gas. X-rays also probe the region near a central black hole, where gas can be heated, ionized, and torn apart before it disappears. In a spiral galaxy, the X-ray sky is a census of recent violence, and it is also a clue to how energy returns to the interstellar medium. Each band is a partial truth, and each can mislead if taken alone. Optical is the starlight we evolved to see, but it misses the cold and the hidden. Infrared is the reprocessed glow of dust, but it needs context to separate heating sources like young stars and older populations. Radio is the map of gas and fields, but it must be translated into mass and dynamics with careful assumptions. X-rays are the signatures of high-energy processes, but they trace only the hottest fraction of matter. Together they form a layered picture of the interstellar medium, like an anatomical scan that reveals different tissues and different contrasts. The interstellar medium is not empty space, and it is not merely background. It is a mixture of gas, dust, magnetic fields, and cosmic rays, threaded between stars and constantly stirred. It exists in phases, from cold molecular clouds only tens of degrees above absolute zero to warm diffuse gas and hot ionized plasma. These phases can coexist side by side, separated by shock fronts, radiation fields, and turbulent boundaries. It is shaped by gravity and by feedback from stars, and it is constantly cycling between states. The arms of M51 are where that cycling becomes organized and visible, because the spiral pattern concentrates material and triggers change. Gravity is the main sculptor, but it works through intermediaries that add texture and unpredictability. In a rotating disk, small perturbations can grow into large-scale patterns, especially when amplified by interactions. Gas responds differently than stars because it can collide, cool, and lose energy, allowing it to pile up. When gas is compressed in an arm, it can fragment into clouds, then cores, then protostars, as radiative cooling lets gravity tighten its grip. Star formation is not random, and it is not guaranteed. It's regulated by pressure, turbulence, magnetic fields, and the balance between collapse and support, a balance that can tip with only slight changes in density. The key ingredients of our story are simple to name and hard to fully model, even with modern computation. Stars provide light, winds, and eventual explosions that inject momentum into their surroundings. Nebulae mark the places where gas becomes luminous under radiation, tracing the youngest clusters like neon signs. Gas and dust provide the mass that can be rearranged and recycled, and they also set the opacity that hides early stages. Gravity provides the long-range force that organises motion and concentrates matter across the disk. Everything else is the consequence of these ingredients interacting over time, with feedback loops that can stabilise regions or push them into bursts. Stellar evolution is the engine of recycling, and it turns simple fuel into complex chemistry. Stars form from cold gas, ignite, and spend most of their lives fusing hydrogen into helium, releasing energy that balances gravity. Massive stars live fast, flood their surroundings with ultraviolet light, and end as supernovae that can outshine entire regions of a galaxy. Lower mass stars evolve more slowly and shed material through winds and planetary nebulae, returning gas gently instead of explosively. In both cases, enriched elements are returned to the interstellar medium, changing the chemistry of future generations. The galaxy is not just forming stars, it is refining its own ingredients. That recycling builds complexity, and it builds it in specific ways that spectroscopy can confirm. Carbon, oxygen, silicon, and iron are forged in stellar interiors and in explosions, then mixed into gas clouds by turbulence and large-scale flows. Dust grains grow in cool outflows and in dense regions, then are shattered by shocks and rebuilt again, cycling like microscopic geology. Over cosmic time, a spiral galaxy becomes a factory that turns primordial hydrogen and helium into the ingredients for planets and life. M51 is far away, but it is part of the same chemical story as the Milky Way, and its light carries evidence of that shared ancestry. M51 also offers a laboratory we cannot replicate at home, because our position inside the Milky Way is both a gift and a constraint. From within the disk, our view is blocked by our own dust and limited by perspective, like trying to map a forest while standing among the trees. We can study nearby star-forming regions in exquisite detail, but we struggle to see the full spiral pattern and to measure global flows cleanly. In M51, we can observe the entire disk at once and connect local processes to global structure. It becomes a mirror that helps us interpret our own galaxy's history, and it reminds us that our home is one example among many. There is also a human history in how this galaxy entered our awareness. M51 was among the early nebulae catalogued by 18th century observers, long before anyone knew galaxies were separate island universes. In the 19th century, sketches revealed spiral structure, and the idea of rotating stellar systems began to harden into science. Only in the 20th century did the distance scale settle, and the Whirlpool moved from curiosity to neighbour in a larger cosmic map. That shift matters, because it shows how interpretation evolves as instruments improve. What looks like a smudge can become a dynamic system once resolution and physics catch up. Yet the mirror is not perfect, and that imperfection is part of the lesson. M51's interaction with its companion makes it more dramatic than many isolated spirals. The tidal encounter can boost star formation, reshape arms, and funnel gas inward along disturbed orbits. It can also stir the central region, feeding whatever lies at the core and altering the balance between calm rotation and inflow. This is why M51 matters as a case study. It shows how environment and interaction can accelerate a galaxy's evolution, and it hints at what the Milky Way might experience in different circumstances. As we move inward, the physics changes in predictable ways, and the visuals tighten. Orbital speeds rise toward the center and shear becomes stronger, stretching clouds and sharpening boundaries. Gas clouds collide more often, and pressure increases, so compression can become both more efficient and more destructive. Star formation can become more intense, and feedback can become more disruptive, carving cavities and driving turbulence. The central region is where the disk's orderly rotation meets the chaos of high density and rapid energy exchange. It is also where small differences in conditions can decide whether gas forms stars or falls deeper. The mystery is that the most important forces are often invisible, and yet they leave measurable signatures. We cannot see gravity, but we can see its effects in rotation curves and in the shapes of arms, where orbital speeds refuse to match visible mass alone. We cannot see dark matter directly, but we infer its presence from motions that luminous mass cannot explain, as if an unseen scaffold holds the disk together. We cannot see magnetic fields with our eyes, but we detect their alignment and their influence on charged particles through polarization. The spiral pattern is a visible outcome of hidden constraints, and it invites a question. How much of what we admire is governed by what we cannot see? The closer we get to the nucleus, the more the story hints at a deeper engine, not just a brighter cluster of stars. Many galaxies host supermassive black holes, millions to billions of times the Sun's mass. Even when quiet, they shape their surroundings through gravity and occasional bursts of activity that can heat gas and launch outflows. If gas falls inward, it can heat up, radiate, and lose angular momentum, spiraling toward an event horizon that never reflects light back. The core of M51 is luminous, and it may also be restless, with energy emerging from processes that are compact and extreme. We will not treat the centre as a single point, because the nucleus is a region with structure and competing processes. We will treat it as a zone where orbits crowd, where gas can pile up, and where star formation and accretion can compete for the same fuel. We will look for signs of shocks, jets, and hot plasma, and we will compare them to calmer zones in the disk. The goal is to understand how a spiral galaxy maintains its structure while constantly transforming its material. In that transformation, stability and violence are not opposites, they are partners. This journey is also about method, because the story of M51 is assembled from many kinds of evidence. We will rely on measurements from space telescopes and ground observatories, and on simulations that test physical assumptions under controlled conditions. We will translate photons into temperatures, densities, and velocities, and we will admit uncertainty where data are incomplete. We will watch how different wavelengths agree and where they disagree, because disagreement is often where the physics is richest. The galaxy is far, but the laws are local. Physics here and physics there are the same, and that is why inference is possible. The Whirlpool Galaxy, seen from 23 million light-years away, is a snapshot of a living system. Its arms are both pathways and records, tracing where gas has been compressed and where stars have recently formed. Its companion is both neighbour and disruptor, shaping the pattern we admire and stirring the disk into renewed activity. Its centre is both beacon and question, promising a different regime of gravity and energy. When we look at it, we are not only seeing a place, we are seeing a process caught midstream. Our hook is simple and unsettling, because it turns beauty into evidence. A spiral can look calm from a distance, like a design etched into darkness and held in perfect balance. Up close, the same structure is built from collisions, radiation, and collapse, with dust lanes marking stress and blue clusters marking brief triumphs. If we could fall inward along one arm, would we find a cradle that keeps making stars, or a monster that consumes the fuel? The answer depends on how matter moves, cools, ignites, and sometimes disappears, and on whether feedback regulates the flow or drives it into runaway extremes. Now we choose a single spiral arm as our guide, and we begin moving along it toward the core. The next chapter follows the arm's dust lanes and star-forming knots, where the galaxy's visible beauty is assembled from hidden gas. We start where the disk is wide and the conditions are gentler, and we let the arm lead us inward. We enter M51, where the arms look calm and the calm is misleading. From a distance, the spiral seems painted onto the sky, yet every bright streak is a record of matter in motion. The spiral is a map of orbits, and those orbits are governed by gravity acting over tens of thousands of light-years. To follow the arm inward, we need the galaxy's blueprint in plain physics, simple rules that produce complex repeating shapes. The first thing the camera reveals is scale. A single arm spans distances that dwarf the solar system by factors that are hard to hold in mind, and the light we see left M51 long before modern astronomy existed. Even so, the arm's geometry is not arbitrary. It is the visible surface of a rotating disk, and rotation is never just rotation. Rotation is a balance between inward gravity and outward orbital inertia, played out in a thin sheet of stars and gas. A spiral galaxy is built in layers that behave differently over time, almost like climates stacked in altitude. The disk is a rotating, flattened system where most stars and gas reside, and it is the part that can stay cold enough to form new stars. The bulge is a central concentration of older stars with hotter, more random orbits, which makes it look smoother and less structured. The halo is a sparse, extended component of old stars and globular clusters, and it reaches far beyond the bright disk. The halo also sits inside a much larger dark matter halo that dominates mass, shaping the gravitational field even where little light is seen. That dark matter halo is not a decorative add-on. It sets the rotation curve, It stabilizes the disk against some instabilities, and it helps determine whether a disk can survive repeated encounters. In the simplest terms, dark matter provides extra gravity without extra starlight, an invisible scaffold that keeps outer regions moving faster than luminous matter alone would allow. When astronomers first measured unexpectedly flat rotation curves in the 20th century, they were forced to accept that galaxies are not made only of what shines. M51, like most spirals, is therefore a luminous disk embedded in a much larger unseen mass distribution. This architecture matters because spirals are not the default galaxy shape across cosmic history. Elliptical galaxies are more spheroidal, with little cold gas and weak ongoing star formation, so their light is dominated by older, redder stellar populations. Irregular galaxies lack stable symmetry and often reflect recent disturbance or low mass, so their star formation can be patchy and chaotic. In cosmology, these forms track environment, merger history, and gas supply, because gravity assembles structure while feedback and cooling decide what survives. M51 is a spiral because it kept a rotating disk and kept enough cold gas, even while living in a neighbourhood where interactions are common. In the modern picture of galaxy evolution, disks are fragile. A major merger can scramble ordered rotation into random motion, turning a disk into a spheroid and heating the stellar orbits until spiral patterns fade. Smaller encounters can still thicken a disk, stir its gas, and trigger bursts of star formation, leaving signatures that persist for billions of years. So when we see a clean spiral like M51, we are seeing a system that has maintained coherence, despite the universe's tendency toward collisions. That coherence is not static serenity. It is a dynamic equilibrium that must be continually rebuilt. From far away, the arms look like painted bands of stars, as if the galaxy were a pinwheel frozen in mid-spin. The first correction is that the arms are not rigid objects, and they are not made of a single set of stars. Stars and gas orbit through the arms, and the arm pattern can outlive any single star that helps illuminate it. The second correction is that the disk does not rotate like a solid wheel, because gravity does not enforce one shared angular speed. Differential rotation is the key kinematic fact of spiral disks, and it is visible in the simplest orbital math. Inner regions orbit the centre faster than outer regions, because the mass distribution sets orbital speed and because gravity is stronger at smaller radii. If the arms were made of the same material staying together, shear would wind them tighter, just as taffy twists when one hand turns faster than the other. In a few rotations, a material arm would become an impossibly wrapped coil, and the graceful openness of M51 would vanish. The arms we see are too open and too persistent for that simple picture, which means the visible pattern cannot be a permanent set of the same stars. This winding problem is not a minor technicality. It is one of the classic clues that forced astronomers to rethink what spiral structure actually is, and it shaped decades of theoretical work. If a spiral arm were a fixed ridge of matter, differential rotation would destroy it quickly on galactic timescales, which are measured in hundreds of millions of years. Yet spirals are common in the nearby universe, and many look organized rather than shredded. So the arm must be something that can persist while the material changes, or it must be something that repeatedly reforms. The winding problem forces a different explanation for spiral structure, and it naturally leads to two broad families of ideas. Either the arms are patterns that persist while material flows through them, or they are transient features that recur as the disk continually reshapes itself. Both ideas can be true in different regimes, and both can be tested with observations that track gas flow and star formation timing. M51's grand design appearance suggests a strong organizing influence, because its two main arms are prominent, coherent, and unusually symmetric. The classic organizing idea is the spiral density wave, developed in the mid-20th century as astronomers tried to reconcile persistent spirals with differential rotation. In this view, the arm is a region of enhanced density that rotates with its own pattern speed, which is not the same as the orbital speed of the gas and stars. Material moves in and out of the wave, like cars passing through a traffic jam that holds its shape even as each car enters and exits. The jam persists even though the cars change, and the arm persists even though its stars and gas are always being replaced. A density wave is not magic, and it is not a solid ridge of matter. It is a gravitational pattern supported by the collective response of many orbits, where small perturbations can align and reinforce each other. Stars respond as nearly collisionless particles, shifting their orbits slightly as they pass through the enhanced gravitational field. Gas responds as a collisional fluid that can shock, cool, and compress, because gas clouds can collide, radiate energy, and lose random motion. That difference is why arms are bright in young stars and dusty along their leading edges, where gas piles up and becomes opaque. To make the idea concrete, imagine the disk as a vast set of nearly circular orbits, each with a slightly different speed. A spiral pattern can be understood as a wave in the density of those orbits, a place where trajectories crowd together for a time before spreading out again. The crowding is gentle for stars, which mostly pass through without colliding, but it is dramatic for gas, which can compress and form shocks. In the shock, kinetic energy turns into heat, and then radiative cooling can remove that heat, leaving denser gas behind. The arm becomes a machine for turning smooth flow into structured clouds. In a rotating disk, there is a special radius where the pattern and the material match, and this is where the geometry of cause and effect changes. At corrotation, gas and stars move with the pattern on average, so the arm is neither overtaken nor overtaking. Inside corrotation, material overtakes the pattern and enters the arm from one side, then exits on the other after being compressed. Outside corrotation, the pattern overtakes the material and the entry side flips, changing where shocks form and where dust lanes appear. These sign changes matter because they set where star formation is triggered and where the offsets between traces should reverse. M51's arms show a telltale sequencing that matches this flow, and the sequence is visible even in modest telescopes. Dark dust lanes trace compressed gas at the arm's upstream edge, where the flow first hits the density enhancement. Bright blue clusters and glowing hydrogen regions appear slightly downstream, where massive stars have already formed and begun to ionize their surroundings. The offset is a clock that times the delay between compression and starbirth, and it turns the spiral arm into a conveyor belt of cause and effect. When we measure that offset carefully, we are measuring time without a stopwatch, using distance and orbital speed as our units. Visually, the arm becomes a layered ribbon. First comes the thin, ink-dark filament of dust, sharply outlined against the stellar background, and then comes a scatter of blue-white knots that look like sparks thrown from a grinding wheel. Around those knots, hydrogen glows in soft pink light, tracing the boundaries of ionized bubbles. Farther downstream, the glow becomes more diffuse, and the arm's edge frays into smaller associations and fading clusters. Even before we explain it, the arm already reads like a sequence, as if the galaxy were writing a timeline across its own disk. Compression alone does not guarantee new stars, because a cloud must become gravitationally unstable before it can collapse. In simple terms, self-gravity must beat pressure and turbulence, so that the cloud's internal motions cannot hold it up. The simplest criterion is the gene's instability, which compares gravity to internal support through temperature and density. When density rises or temperature falls, the gene's mass drops and collapse becomes easier, meaning smaller clumps can become self-gravitating. Spiral arms help by raising density and by driving shocks that remove energy, turning diffuse gas into colder, denser structures. The gene's idea is deceptively simple, and it hides a rich physical story. Temperature is not just a number, but a measure of particle speeds, and cooling is not automatic in space. Gas cools by emitting radiation through atomic and molecular transitions, and the efficiency depends on composition, density, and shielding from starlight. Dust grains help by providing surfaces where molecules can form, and they also absorb ultraviolet photons that would otherwise heat the gas. So when a dust lane thickens, it is not only blocking light, it is also creating the conditions for chemistry and cooling that make collapse possible. In real galaxies, collapse is regulated by more than one number, because the interstellar medium is turbulent, magnetized, and constantly stirred by feedback. Turbulence can support a cloud by adding internal motions, but turbulence also creates dense filaments that collapse first, because shocks and converging flows concentrate gas. Magnetic fields can resist compression by adding magnetic pressure and tension, but they can also guide flows into elongated structures and help remove angular momentum from collapsing cores. Feedback from young stars can disrupt clouds with radiation, winds, and supernovae, yet it can also compress nearby gas and trigger secondary collapse. The arm is where these competing effects are organized into repeated cycles, so the same region can both form stars and erase the evidence of their birth. A second instability operates on the scale of the disk itself, where gravity competes with shear and pressure across kiloparsec distances. If gas and stars in the disk become too self-gravitating, perturbations grow into clumps and segments, and the disk stops behaving like a smooth fluid. The tomb stability idea captures this balance between self-gravity, pressure, and shear, offering a criterion for when a rotating disk can resist collapse. Strong shear can tear structures apart before they grow, while strong self-gravity can overcome shear and amplify small disturbances. Spiral arms can be both the product of these instabilities and the trigger that sharpens them, because an arm concentrates mass and changes local conditions. The tumor picture also helps explain why star formation is not uniform across a disk. Even if gas is present everywhere, only some regions cross the threshold where gravity wins over stabilizing forces. In a grand design spiral, the arm can push regions over that threshold repeatedly, producing a rhythm of star formation that follows the pattern. This is why the arm can look like a luminous chain of beads, with clusters spaced along it like knots on a rope. The spacing is not random. It reflects the physics of fragmentation in a rotating, self-gravitating medium. The interstellar medium is the arm's raw material, and it is not a single substance. Cold molecular gas is dense and cold enough for star formation, and it hides in dusty clouds where starlight is absorbed and re-emitted in infrared. Warm neutral gas fills much of the disk volume and acts as a reservoir, more diffuse and less immediately star-forming. Warm ionized gas glows around young stars where ultraviolet radiation strips electrons from hydrogen, creating H2 regions that mark recent massive star formation. Hot ionized gas is a thin plasma heated by supernova shocks and stellar winds, filling cavities and chimneys that can vent energy into the halo. These phases are not neatly separated like layers of a cake. They mix, they exchange mass, and they transform into one another as energy is injected and radiated away. A molecular cloud can be eroded into warm neutral gas by ultraviolet photons, and warm neutral gas can cool and recombine into molecular form if it becomes dense and shielded. Supernovae can heat gas to millions of degrees, and then that gas can cool over time, raining back into the disk or mixing into the halo. The arm is where these transformations are accelerated, because compression and feedback are both stronger there. Each phase is traced by different wavelengths, so no single image tells the whole story, and this is where the documentary's visuals can become almost forensic. Molecular gas is mapped with CO emission as a proxy for H2, because H2 is hard to detect when cold and not excited. Ionized hydrogen is traced by H-alpha emission, marking regions around massive young stars whose lifetimes are short enough to time recent events. Radio continuum traces relativistic electrons and magnetic fields, often linked to supernova remnants and the broader cosmic ray population. X-rays trace the hottest gas and compact sources, revealing where energy was recently injected and where stellar remnants or accreting objects may be present. In M51, these traces line up in a pattern that explains the arm's appearance, and the alignment is a powerful test of the underlying physics. So concentrates along the dust lanes where gas piles up, and the emission often appears as clumpy complexes embedded in a larger ridge. H-alpha and blue light peak downstream, where massive stars have already formed, clearing cavities and lighting their surroundings. Radio continuum can extend further because cosmic rays diffuse and magnetic fields thread the disk, smoothing out the signal over larger distances. X-rays appear in bubbles and point sources, marking the aftermath of stellar death and the hot interiors of superbubbles. When we overlay these maps, the arm becomes a multi-wavelength storyboard. The dust lane is the opening frame, dense and cold, where the gas is being prepared. The CO ridge is the next frame, showing where molecules dominate and where clouds are assembling. The H-alpha glow is the next, announcing that massive stars have already ignited and that their ultraviolet light is reshaping the neighbourhood. The radio and X-ray emission are the later frames, showing that some of those massive stars have already ended their lives, leaving behind shock waves and energetic particles. The arm therefore contains both creation and destruction at once, and the two are inseparable. Massive stars form quickly, shine intensely and die within a few million years, which is a blink compared to a galactic orbit. Their winds and supernovae carve cavities and drive shocks into surrounding gas, creating expanding shells that can be seen as arcs and bubbles. Those shocks can disperse a cloud, ending one episode of star formation by unbinding the gas. They can also compress neighbouring gas, seeding the next episode by pushing it over the threshold of instability. The tranquil spiral is really an engine that runs on gradients, differences in density, pressure and velocity that are constantly being renewed by rotation. Gas enters the arm, is compressed, cools, and fragments into clouds, and the fragmentation proceeds along filaments where gravity can focus collapse. Dense cores collapse into protostars, then ignite into luminous clusters that begin to alter their environment almost immediately. Radiation and explosions then return energy and momentum to the medium, stirring turbulence and heating gas, while some material is expelled and some is recycled. The cycle repeats as fresh gas continues to flow through the pattern, making the arm a standing wave in a moving sea. This is why arms can look orderly while hosting continual violence, and why the word calm is so deceptive. The order comes from orbital dynamics and long-range gravity, which acts smoothly and predictably across the disk. The violence comes from short-range gas physics and stellar feedback, which act locally and explosively inside clouds. The arm is the interface where the two meet and stay coupled, so that a stable pattern can be built from unstable material. In a sense, the spiral is a compromise between what gravity wants on large scales and what gas does on small scales. Historically, this realization changed how astronomers interpreted galaxy photographs. Early images suggested that arms might be permanent structures, like spokes on a wheel, and the winding problem made that interpretation untenable. The density wave concept offered a way to keep the pattern without freezing the matter, and it connected spiral structure to measurable kinematics. Later, numerical simulations showed that disks can also generate transient spirals through instabilities, with arms that form, break, and reform while still producing organized star formation. The debate became less about choosing one mechanism and more about identifying which dominates in a given galaxy. M51's environment adds another layer to the blueprint, and the visuals make that environment hard to ignore. The companion galaxy, NGC 5195, sits close by, and its gravity tugs on M51's disk, producing tidal forces that distort orbits. Those tides can amplify spiral structure, strengthening density enhancements and making the arms more coherent. They can also drive streaming motions that redistribute angular momentum, subtly changing how gas and stars circulate. Over time, such torques can help funnel gas inward, feeding the inner disk and potentially the central regions. This interaction is not just a background detail for later chapters, because it is part of why M51 is such a textbook spiral. A strong perturbation can lock in a grand design pattern more easily than an isolated disk, because the companion provides a repeating gravitational nudge. The companion can also trigger bursts of star formation by raising gas density, and by compressing the disk along specific lanes. In that sense, M51's beauty is partly an afterimage of gravitational stress, a visible signature of an encounter that is still unfolding. When we admire the symmetry, we're also looking at the consequences of disturbance. The inward funneling matters because the center is where the story will tighten and where timescales shrink. Gas that loses angular momentum can drift towards smaller radii, and that drift can be driven by spiral torques and tidal perturbations. As it moves inward, orbital times shorten and shear strengthens, so the environment becomes more extreme. Collisions between clouds become more frequent, and pressures rise, changing the balance between collapse and disruption. The same processes that light the arms can become more intense near the nucleus, where the disk is denser and the gravitational potential is steeper. To keep the physics grounded, we translate the arm into measurable quantities, because a pattern is only as real as what it predicts. Rotation curves give orbital speed as a function of radius, revealing how mass is distributed and how strongly dark matter contributes. Streaming motions along the arm show where gas is slowed and compressed by the pattern, leaving signatures in Doppler-shifted spectral lines. Line widths and line ratios estimate temperature, turbulence, and ionization, letting us infer the energy state of the gas. Offsets between tracers measure timescales for cloud collapse and feedback, turning spatial separations into chronological delays. These measurements also test whether density waves are long-lived or transient, and they do it in a way that is surprisingly direct. If a single pattern persists, offsets and streaming should be coherent over large scales, and the pattern speed should be relatively well defined. If arms are short-lived and recurrent, signatures may vary with radius and time, and the disk may host multiple overlapping patterns. Many modern simulations produce transient spirals that continuously form and dissolve, driven by gravitational instabilities and swing amplification. M51 may sit between these extremes, with tides sustaining a stronger pattern even as local segments evolve. The deeper mystery is that the arm's brightness is not a mass map, and the camera can mislead as easily as it reveals. Blue light highlights short-lived massive stars, which are a small fraction of stellar mass but dominate the optical glow. Dust lanes hide starlight and can make regions look empty, even when they contain enormous amounts of cold gas. Infrared reveals embedded star formation that optical light misses because dust re-radiates absorbed energy at longer wavelengths. A spiral arm is therefore a biased view of where matter is, and understanding it requires constant translation between what we see and what is physically there. This bias is also why multi-wavelength astronomy became essential to studying spirals. Optical images alone emphasize the youngest stars and the sharpest dust features, which makes arms look like pure star-forming ridges. Radio and millimeter observations reveal that much of the mass is in cold gas, often arranged in complexes that do not glow brightly in visible light. Ultraviolet highlights even younger populations, while infrared shows where star formation is still buried in dust. By combining these views, we replace a single, seductive picture with a layered physical model, so we keep returning to the same central question that drives the journey. What physical processes shape M51 from its arms down to its centre over cosmic time? The arms are our first close look at that machinery in action, because they are where large-scale dynamics and small-scale physics meet. They show gravity organising motion, and gas physics turning motion into stars, and feedback preventing the process from running away. They also show how an external companion can tune the whole system, strengthening patterns that might otherwise be weaker. We move along the arm from bright clusters into darker lanes, and the sequence becomes clearer the closer we look. Dust marks the compression front where gas is forced into denser states, and the dust is mixed with molecules that can cool efficiently. Downstream, newborn stars ionize hydrogen and announce their arrival, and their radiation begins to carve the first cavities. Farther still, supernovae and winds erase the evidence and stir the medium again, leaving hot bubbles and turbulent wakes. The arm is a timeline written across space, and the writing is done in multiple wavelengths. The disk, bulge, and halo provide the stage, but the arm provides the plot because it is where the action repeats. Differential rotation supplies shear that would destroy any rigid feature, forcing the spiral to be a pattern rather than a fixed structure. Density patterns and instabilities supply a way to keep spirals visible, either as long-lived waves or as recurring transient segments. The interstellar medium supplies fuel that can be compressed into stars, and its phases determine what can cool and collapse. Feedback supplies the counterforce that prevents collapse from consuming everything, keeping the galaxy in a regulated, self-renewing state. M51's companion adds the external push that makes these patterns louder, and it does so without rewriting the basic rules. Tidal forces can strengthen arms and drive gas inward, and they can also create asymmetries that later relax into new configurations. That inward drift sets up the next chapters, where the environment becomes denser and more extreme, and where the same physics will reappear with higher stakes. When gas accumulates toward the center, the cycle of compression, collapse, and feedback can accelerate, and the consequences become harder to ignore. Now we follow a dust lane as it curves along the inner edge of the arm. The lane is not just darkness, and it is not just obscuration, even though it looks like a shadow drawn across starlight. It is cold gas in transition, on the verge of collapse, and it is dense enough to shield itself from the galaxy's ultraviolet glare. Along its length, the lane breaks into knots and scallops, hints of clouds forming within a larger flow, as if the arm were gathering itself into seeds. As the lane arcs inward, the background changes, and the arm's bright clusters fall behind us. The starlight becomes more crowded, and the disk's texture grows finer, because we are looking through more layers of stars. The dust lane, however, stays sharply defined, because it is a real concentration of mass, not a trick of perspective. Where it thickens, it reddens the light behind it, and where it thins, it reveals a faint glitter of older stars. The visual contrast is telling us where the gas is densest, and where the next generation is being prepared. We track it into a nebula, toward the hidden nurseries where star formation actually begins. The nebula is not only a pretty glow, because it is a boundary between phases of the interstellar medium. Ionized gas outlines the region where young stars have already switched on, while molecular gas and dust remain tucked behind the bright edge. The scene is a cross-section of the cycle: cold material feeding collapse, hot radiation marking the outcome, and turbulent interfaces where the two meet. The arm has answered one question and opened another, and that is the rhythm of this journey. It explains why spirals can persist without being rigid structures, because patterns can survive even as matter flows through them. It also shows that the galaxy's calm appearance is a mask over constant change, because every bright cluster implies a recent collapse and every bubble implies a recent explosion. If the arms can organize creation at the edges, what happens when the flow reaches the center, where gravity tightens and the environment grows harsher? We continue inward, using the dust as our guide and the physics as our map, because the lane is both a visual feature and a dynamical clue. The next step is to enter the clouds themselves, where gravity competes with heat, turbulence, and magnetic fields, and where collapse becomes a local, measurable process. There, the galaxy's blueprint becomes a birth process, and the spiral pattern becomes a factory line, turning orbital motion into stars one cloud at a time. We cross the arm's dust lane and enter the nebula that optical light only outlines. The spiral pattern still guides the flow, but the real action is hidden inside cold gas. In visible light, the arm looks like a painted ribbon, yet in longer wavelengths it becomes a layered landscape of shadows, embers, and buried heat. As we pass through it, this scene thickens, starlight dims, contrast rises, and the arm's dark braid resolves into overlapping sheets and knots. A star-forming region is not empty space with a few bright knots. It is a layered medium of molecules, dust grains, magnetic fields, and turbulent motion. The emptiness we imagine is an illusion of scale. Between particles there is vast distance, but the collective behaves like a fluid with memory and structure. That memory is physical. Shocks, shears, and magnetic tension leave patterns that persist long after any single collision. In M51, that structure is organized by the spiral arm's passage through the disk. Gas streams into the arm, slows, and compresses, much like cars bunching in a traffic wave. The compression does not instantly make stars, because the gas must first change phase, cool, and become molecular. Before it can collapse, it must also shed energy efficiently, and it must do so while being jostled by the galaxy's rotation. The dominant reservoir is molecular hydrogen, H2, which forms where gas is shielded. Ultraviolet starlight easily breaks H2 apart, so the molecule survives only where dust and self-shielding reduce the radiation field. We trace it indirectly through CO emission, because cold H2 is hard to excite. In practice, astronomers read H2 through its companions, the way you infer wind by watching leaves rather than air. That indirectness is not a minor technicality, it shapes how we map galaxies. Carbon monoxide is rare compared with hydrogen, yet it radiates efficiently at millimeter wavelengths, and its rotational lines carry information about temperature, density, and motion. By calibrating CO brightness to H2 mass, astronomers build a working census of the hidden fuel. The calibration is imperfect, because CO can be faint in low metallicity gas, yet it remains our most reliable signpost across spiral disks. These molecular clouds are cold by Earth standards and colder than most of the galaxy. Typical temperatures sit around 10 to 30 Kelvin, only a few tens above absolute zero. At these temperatures, thermal speeds are low, and chemistry proceeds slowly, but the physics becomes exquisitely sensitive to small energy exchanges. A tiny change in heating or shielding can decide whether a clump stays diffuse or begins to fragment. Cold does not mean simple or calm, because the gas is constantly stirred. Supersonic turbulence creates density fluctuations that can both support clouds and seed collapse. In a cloud, turbulent eddies crash and shear, shocks form where flows converge, and rarefied pockets open where motions diverge. The cloud becomes a weather system measured in parsecs, with fronts, vortices, and sudden compressions. The turbulence is supersonic, because the sound speed in 10 Kelvin gas is only a few tenths of a kilometer per second. Motions of several kilometers per second therefore generate shocks that compress gas abruptly, raising density without necessarily raising temperature for long. Cooling is so efficient that the gas can radiate away shock energy and remain cold. Molecules and dust act like radiators, turning mechanical violence into faint infrared and millimeter photons. The densities vary across orders of magnitude, from diffuse envelopes to compact cores. A cloud's average may be hundreds of particles per cubic centimeter, while cores reach millions. Those numbers still sound sparse by earthly intuition, yet over light years they amount to immense mass, and gravity integrates every particle's pull. In a core, the difference between stability and collapse can be a modest rise in density, sustained for only a fraction of a million years. Composition is mostly hydrogen and helium, with a small but crucial fraction of heavier elements. Carbon and oxygen enable cooling lines, and metals help the gas shed energy. In astrophysics, metals means everything heavier than helium, atoms forged in earlier generations of stars, then returned by winds and explosions. Even a trace abundance matters, because a few efficient emitters can dominate the cooling budget. That historical inheritance matters inside a nebula. Without carbon, oxygen, and dust, the gas would cool less efficiently and resist fragmentation, changing the entire spectrum of stars produced. Star formation is therefore a chemical story, as well as a gravitational one. Today's clouds remember yesterday's supernova. When we look into M51's arm, we're also looking into an archive of prior stellar lives. Dust is only about 1% of the mass, yet it controls the chemistry. Grain surfaces catalyze H2 formation, and grain opacity blocks ultraviolet heating. Each grain is a microscopic solid, often a silicate or carbon-rich particle, coated with icy mantles in the coldest regions. Under magnification, the dark lane becomes a blizzard of tiny solids, each one altering how light and atoms move. On those surfaces, hydrogen atoms meet and bind, releasing energy that the grain can absorb and re-radiate. In the gas phase, making H2 is far less efficient at these temperatures, so dust becomes the quiet matchmaker of the molecular universe. The same grains also host more complex reactions, building molecules that later become traces of dense gas. Some of those molecules, like ammonia or formaldehyde, act as thermometers, letting observers estimate conditions from afar. Dust also provides a cooling pathway by coupling gas to infrared emission. When dust absorbs starlight and re-radiates, it helps the cloud stay cold enough to fragment. In dense regions, collisions between gas molecules and grains transfer heat, and the grains then leak that energy away as long-wavelength photons. The cloud's temperature is not set by one source, but by a balance. Cosmic rays, starlight, and internal dissipation all compete with radiative escape. From far away, dust looks like a dark lane that hides stars. Up close, dust is the thermostat and the chemical lab that makes star formation possible. The lane is not merely a silhouette, it is a map of where photons are stopped, where molecules survive, and where gravity can work in relative darkness. When the camera lingers on the arm, the darkness itself becomes informative, outlining the places where the galaxy is most alive. Inside the cloud, structure appears as filaments and clumps rather than smooth spheres. Turbulent shocks and converging flows compress gas into long, dense strands. In infrared and submillimeter images, these filaments resemble braided rivers, with thinner tributaries feeding thicker spines. Their edges are not sharp because density fades gradually into the surrounding medium like mist thinning into air. Some filaments are transient, dissolving as turbulence shifts, while others become persistent because gravity reinforces them. Magnetic fields can align with the strands, and the gas then slides along field lines, collecting where the geometry allows. The result is a network that looks organic, yet follows the strict accounting of forces. The filaments are also hierarchical. Thick trunks host thinner threads, and those threads host the densest cores. Filaments are not decorative because gravity prefers them. Once a filament becomes dense enough, it fragments into regularly spaced cores, each a potential star system. The spacing is not random. Instabilities grow at characteristic scales, setting a rough rhythm of condensation along the filament's length. In images, that rhythm appears as beads on a string, a pattern repeated across the Milky Way and echoed here in M51. The key threshold is simple in words, even if complex in detail. Collapse begins when self-gravity overwhelms internal support from heat and turbulent motion. In practice, that balance depends on geometry, magnetic fields, and how quickly the gas can radiate away energy as it compresses. If the gas cannot cool, compression raises pressure and the collapse stalls, but if it can cool, gravity keeps gaining ground. Thermal pressure comes from particle speeds, which rise with temperature. Turbulent support comes from chaotic motions, which act like an extra pressure on larger scales. Turbulence can also do the opposite, by creating dense peaks. It can hand gravity a foothold where collapse begins first. This dual role is why clouds can look stable in bulk, while still forming stars in localized pockets. The genes idea captures the balance without heavy math. If a region is cold and dense enough, gravity wins and the region cannot hold itself up. In that picture, there is a critical mass and size. Above it, the region is unstable, and below it, internal motions can resist contraction. The concept dates back to James Jeans in the early 1900s, when astronomers were first trying to connect gas physics to the existence of stars. Historically, this framework traces back to early 20th century attempts to understand why stars form at all. Jeans treated gas as a continuous medium, and later work added the messy realities of cooling, turbulence, and magnetic fields. The core insight remains: gravity is patient, and given the right conditions, it eventually dominates. In modern simulations, that patience plays out as a slow gathering, followed by a rapid plunge once a core tips past stability. Compression in the spiral arm pushes gas toward that threshold. Cooling by molecules and dust lowers the internal pressure, so smaller clumps can become unstable. The arm's dust lane often marks the upstream edge of this process. Dense gas gathers there before star formation lights up downstream. The offset is subtle in a still image, yet in motion it reads like a cause and effect trail across the arm. In M51, the geometry is especially readable because the spiral pattern is grand and coherent. Observers compare the location of CO ridges, dust lanes, and H2 regions to infer a time sequence. The offsets are a kind of galactic stopwatch, how far the gas travels while chemistry and collapse proceed. That stopwatch depends on rotation speed, arm pattern speed, and the local strength of the spiral shock, so the same arm can host slightly different timelines at different radii. Magnetic fields complicate the picture because they add stiffness to the gas. Field lines resist being bent and compressed, and they can slow collapse across them. In dense gas, ions are tied to the magnetic field, and through collisions they can drag neutral molecules along, partially coupling the whole cloud to the field. Even when the field is weak, it can redirect flows, turning what would be a direct plunge into a guided anisotropic drift. That coupling is not perfect, and it weakens as density rises. Neutrals can drift relative to ions, a process often called ambipolar diffusion, allowing gravity to slip past magnetic support over time. The pace of that drift can influence how quickly cores form and how long clouds survive. In the densest pockets, the field may still thread the gas, but it can no longer enforce order on every particle. Yet magnetic fields also guide flows along preferred directions. They can help shape filaments, and they can channel material into cores where gravity is already strong. In polarization maps, dust emission can reveal field orientation, turning the invisible geometry into a measurable pattern. The lines we draw on such maps are not literal threads, but statistical alignments. Many grains, many photons, one coherent direction. As collapse starts, the cloud does not fall straight inward like a clean textbook sphere. Real cores rotate, and rotation becomes more important as the radius shrinks. Even a slight initial spin, seeded by turbulence or shear in the larger cloud, becomes amplified as matter moves inward. The visual changes with scale. What begins as a lopsided clump becomes a flattened, rotating structure with a clear axis. Angular momentum is conserved, so spin speeds up during contraction. The result is a flattened accretion disk around the forming protostar, not a simple point. The disk is a compromise between gravity pulling inward and rotation insisting on orbit, and it becomes the stage for later planetary architecture. In the disk, temperature and density vary sharply with radius, creating chemical zones that later influence what solids can form. A protostar is not yet a stable star because fusion has not fully ignited. It shines mainly from gravitational energy released as gas falls inward and heats up. The luminosity is an accounting of infall. Each kilogram of gas releases energy as it descends the gravitational well, and that energy must go somewhere. Over time, as the core heats and compresses, the balance shifts toward nuclear burning, but the early light is powered by collapse itself. In the earliest phase, the protostar is deeply embedded, wrapped in an envelope of infalling material. Photons struggle to escape, so energy emerges at long wavelengths, where dust is more transparent. What looks dark in optical light can glow softly in the far infrared, like heat seen through fog. If we could see in those wavelengths with our eyes, the dust lane would look less like absence and more like a muted internal fire. Accretion is the growth mechanism, and it is messy. Gas spirals through the disk, loses angular momentum through turbulence and magnetic stresses, then lands on the protostar. The disk is not a calm ring. Its gas can be unstable, clumpy, and time variable, producing bursts of accretion that change the protostar's brightness. Those bursts may be brief compared with a star's lifetime, yet they can dominate the mass budget, arriving in sudden, luminous episodes. Those stresses are often described through an effective viscosity, but the underlying physics can involve magnetorotational turbulence and spiral density waves. In plain terms, the disk must find a way to move angular momentum outward so mass can move inward. Without that transport, the protostar would starve despite being surrounded by fuel. This is one of the disk's central paradoxes. Material must lose something it cannot easily shed, and the disk invents instabilities to do it. The disk is also where planets will eventually assemble if the system survives long enough. Dust grains stick, grow, and settle, building the first solid scaffolds. Collisions can both build and break grains, and the outcome depends on speed, composition, and whether icy coatings make particles more adhesive. The earliest growth is microscopic, but it sets the stage for later leaps when gravity begins to matter for solids as well. As grains grow, they begin to decouple from the gas and drift, concentrating in pressure bumps and rings. Those concentrations can become the seeds of planetesimals, the kilometre-scale bodies that later collide into planets. In this way, the chemistry of a cold cloud echoes into the geology of future worlds. The same carbon and oxygen that cooled the parent cloud can later become rock, water, and atmosphere, reshaped by a different set of forces. But the disk is not only a nursery for planets, because it launches outflows. Magnetic fields anchored in the disk can fling material outward in collimated jets. The jet is a narrow beam, often moving hundreds of kilometers per second, and it carries away angular momentum that would otherwise keep gas from accreting. In images of nearby star-forming regions, these jets appear as needle-straight lines, punctuated by bright knots where the flow pulses. Bipolar jets carve channels through the surrounding envelope. They remove angular momentum and energy, and they regulate how quickly the protostar can gain mass. Where the jet slams into ambient gas, it creates shock-excited knots, and those knots can glow in infrared lines of molecular hydrogen and other species. The outflow is therefore both a symptom and a control mechanism, evidence that accretion is happening and a tool that makes further accretion possible. Outflows also inject momentum back into the cloud. They can stir turbulence, disrupt nearby cores, and sometimes compress gas at the edges of their cavities. In crowded regions, many outflows overlap, and the cloud becomes a battlefield of competing pushes and pulls, gravity gathering, feedback dispersing. The cloud's internal structure begins to look sculpted, as if carved by invisible chisels that strike from within. This is the first appearance of the chapter's paradox in physical form. The same collapse that makes a star also powers the feedback that can halt further collapse. The newborn object is both product and agent, and its growth is shaped by the disturbance it creates. One can ask, watching this balance play out across a spiral arm, how many stars are prevented for every star that succeeds? Protostellar evolution proceeds through stages that telescopes can distinguish. Deeply embedded objects glow in far infrared, while more exposed young stars brighten in near infrared. As envelopes thin and disks dominate, the spectral energy distribution shifts, and the system's light becomes less reprocessed by dust. Those stages are not rigid boxes, yet they provide a practical language for comparing regions that differ in age and obscuration. From 23 million light-years away, we cannot resolve individual disks in M51. We infer their presence through integrated light, spectral energy distributions, and statistical populations. The galaxy becomes a laboratory where we trade detail for scale, many regions at once, each contributing a piece to the overall pattern. It is a different kind of clarity, where individual stories blur, but the collective physics becomes unmistakable. Infrared is the main window because it penetrates dust better than visible light. Warm dust around young stars re-radiates strongly, turning hidden clusters into infrared sources. In images, these regions appear as compact embers embedded in darker lanes, hinting at activity still wrapped in its natal cocoon. The glow is not uniform, because dust temperature depends on distance from the stars, producing gradients that trace the geometry of cavities and dense clumps. Radio and millimeter maps show where the raw material sits. CO line emission traces molecular gas mass, and line widths hint at turbulence and cloud dynamics. With modern interferometers, astronomers can separate giant molecular associations into smaller complexes, measuring how gas piles up along the arm. The maps feel almost topographic, ridges, valleys, and plateaus drawn not in height, but in column density and velocity. Line widths are not just a blur, they encode motion. Broad lines can indicate turbulence, overlapping clouds along the line of sight, or systematic flows driven by spiral shocks. By mapping velocity across a region, we can watch the cloud's internal weather, even when the cloud itself is invisible in optical light. A gradient across a cloud can reveal shear, while a sudden jump can betray a shock, like a cold front crossing a continent. Optical emission lines trace the exposed consequences of starbirth. H-alpha marks ionized hydrogen around massive young stars, and O3 highlights hotter, more excited regions. These lines are not merely colours, they are fingerprints of electron temperatures, densities, and the hardness of the radiation field. Their ratios can even hint at how porous the surrounding gas is, and whether ionizing photons are escaping into the wider interstellar medium. These ionized zones are called H2 regions, and they expand as radiation heats the gas. Ultraviolet photons strip electrons, and recombination produces the characteristic glow. The physics is a steady cycle: ionization by starlight, recombination in the gas, and emission of photons that escape as visible nebular light. The expansion speed depends on density and temperature, so each H2 region is a local experiment in pressure and confinement. The expansion creates pressure-driven fronts that eat into the molecular cloud. The bright nebular edge is therefore a moving boundary between cold fuel and hot feedback. At that boundary, dense clumps can survive as pillars and globules, their surfaces photo-evaporating under ultraviolet assault. The shapes can look sculptural, yet they are simply the survival patterns of density, where the thickest pockets resist the longest. Massive stars dominate this boundary even though they are few. The stellar initial mass function produces many low-mass stars, but only a small fraction become massive. Most of the mass may end up in modest stars, yet most of the radiative power comes from the rare giants. This skewed distribution is one reason galaxies can look calm in mass while blazing in light, because luminosity is weighted toward the upper end. Massive stars are rare because assembling them requires sustained accretion against strong radiation pressure. Their formation is also sensitive to environment, density, and fragmentation. In dense clusters, competitive accretion and mergers of gas flows may help, but the details remain an active field. Nature's most luminous stars are still partly mysterious. Even in our own galaxy, where we can observe individual regions, the earliest phases are so obscured that theory must fill in gaps. Yet once they exist, they control the energy budget. A single O-type star can outshine thousands of Sun-like stars and flood the region with ultraviolet light. That light heats dust, ionizes gas, and changes chemistry, turning a quiet molecular environment into a bright, expanding cavity. The transformation can be abrupt, as if a hidden room suddenly had its light switched on, revealing walls that were always there. This imbalance drives the chapter's tension at larger scales. The stars that light the arm are the ones most capable of destroying the clouds that made them. Their lifetimes are short, but their influence is immediate, and the surrounding gas responds on timescales comparable to the star's own evolution. The arm becomes a place where creation and erosion are not separate chapters, but simultaneous lines of the same script. Star formation therefore tends to occur in groups, not in isolation. Molecular clouds fragment into many cores, producing clusters and associations with shared ages and chemistry. In a cluster, stars form from the same reservoir, so their elemental abundances match closely, like siblings born from one well-mixed cauldron. Their motions also begin correlated, although the cluster may later disperse, releasing its members into the disk. Clusters matter because they concentrate feedback in one place. Many winds and radiation fields overlap, creating superbubbles that are larger than any single star's influence. The combined pressure can punch holes in the surrounding medium, venting hot gas upward and leaving behind shells that sweep the disk. In multi-wavelength views, those superbubbles show layered structure: hot X-ray interiors, warm ionized rims, and cold molecular fragments pushed to the edges. Stellar winds add another feedback channel before any supernova occurs. Fast outflows from massive stars push on the gas, carve cavities, and generate shocks. These winds carry momentum and mechanical energy, and their interaction zones can glow in X-rays where gas is heated to millions of degrees. The windblown cavity is not empty, because it is filled with tenuous, overpressured plasma that presses outward like a balloon. As bubbles expand, they sweep up shells of denser material. Those shells can become gravitationally unstable, triggering a second generation of star formation at the rim. The result can look like a ring of new stars around an evacuated center, a pattern that hints at cause and effect without guaranteeing it. The timing matters, because a shell must survive long enough to cool and fragment before it disperses. Feedback is therefore not purely destructive or purely creative. It can quench collapse locally while promoting collapse nearby, depending on geometry and timing. A cloud may be dispersed before it forms many stars, or it may be compressed into a brief, efficient burst. Both outcomes are written in the same physics. The spiral arm supplies the raw compression, but feedback decides how long the compression can keep working. On longer timescales, the most dramatic feedback arrives as supernovae. Massive stars die quickly, often within a few million years, and their explosions inject enormous energy. The blast wave expands supersonically, sweeping up interstellar gas and converting ordered motion into turbulence across many parsecs. The remnant's expanding shell can persist long after the star is gone, a ghostly structure that continues to shape the next generation. A supernova shock heats gas to millions of degrees and drives turbulence. It also accelerates cosmic rays and helps maintain the galaxy's magnetized, energetic background. Those cosmic rays diffuse through the disk, ionizing gas in places where starlight cannot reach, subtly altering chemistry in shielded regions. In dense clouds, that ionization can be small but decisive, because it sets how well the gas couples to magnetic fields. Supernovae enrich the interstellar medium with heavy elements. Oxygen, silicon, and iron are returned to the gas, raising metallicity and changing future cooling efficiency. Each generation of stars therefore modifies the conditions for the next, and the nebula becomes a page in a long chemical history. The dust itself can be replenished and destroyed in these events, making the galaxy's dark lanes a dynamic, evolving component. This connects birth to death in one continuous cycle. Star formation consumes cold gas, and star death returns processed material and kinetic energy to the same medium. The cycle is not perfectly closed, because some gas is expelled to the halo, yet much of it eventually cools and returns. In that sense, the spiral arm is not just a site of production, but part of a circulation system that never fully stops. In M51, this cycle is organized by the spiral arm but not confined to it. Hot gas can vent upward into the halo, and cooled material can later rain back down. The disk and halo exchange matter and energy, and the spiral pattern acts as a repeating organizer within that larger circulation. The arm is a wave in the disk, and the gas is the medium that keeps passing through it, again and again. The rate of star formation is therefore a measurable outcome of competing processes. Gravity gathers gas, cooling allows collapse, and feedback limits efficiency by dispersing clouds. A striking fact emerges from nearby galaxies. Most molecular gas does not turn into stars quickly, implying that support and disruption are usually effective. The inefficiency is not a failure of gravity, but evidence of regulation, as if the galaxy is throttling its own conversion rate. Astronomers infer star formation rates using multiple tracers that each carry biases. H-alpha traces very recent massive stars, ultraviolet traces slightly longer times, and infrared traces obscured regions. Each tracer samples a different clock, because massive stars live briefly, while lower mass populations persist and fade more slowly. Comparing them is like comparing photographs taken with different shutter speeds, each emphasizing a different moment of the same event. Calibrations convert luminosity into a formation rate, but assumptions matter. Dust absorption, stellar population models, and leakage of ionizing photons all shift the inferred numbers. Even the choice of initial mass function changes the result, because the brightest tracers respond mostly to the most massive stars. The uncertainties are not just technical, they remind us that galaxies are not uniform laboratories, and every region has its own geometry and obscuration. CO maps estimate the molecular gas reservoir, and combined with star formation rate they yield a depletion time. This tells us how quickly a galaxy would run out of fuel at current activity. In many spirals, depletion times are measured in billions of years, suggesting that star formation is regulated rather than explosive. The long timescale implies that clouds are repeatedly assembled and dispersed, with only a small fraction of their mass converted in any one episode. M51 is a benchmark because its structure is clear and its distance is manageable. We can compare cloud properties, arm offsets, and feedback signatures across the disk in one system. Its interaction with the companion also provides a natural experiment. Tidal forces amplify the spiral pattern and reshape gas flows. Historically, M51 has been a touchstone since the 19th century, when early telescopes revealed its spiral form and helped establish that nebulae could be entire galaxies. This matters beyond one galaxy, because star formation drives galaxy evolution. Over cosmic time, galaxies convert gas into stars, enrich their medium, and change their ability to cool. The balance between inflow of fresh gas, internal consumption, and outflow from feedback sets the long-term trajectory of a galaxy's brightness and colour. When star formation slows, galaxies redden, not because stars vanish, but because the short-lived blue ones stop being replaced. The conversion is not steady across history, and cosmology provides the context. The universe formed stars more rapidly in the past, then declined as gas supplies thinned and heating increased. Observations of distant galaxies show a peak in star formation billions of years ago, when mergers and abundant cold gas made starbirth more intense. Seen against that backdrop, M51's present-day arms are not a relic, but a continuing, scaled-down version of a once more vigorous cosmic era. Spiral galaxies like M51 show how the process continues in the present era. They sustain star formation by cycling gas through arms, clouds, and feedback-regulated phases. The spiral pattern does not create gas, but it organizes it, compressing, cooling, and then handing it back to the diffuse medium after stars ignite. The arm is therefore an ordering principle, a repeating corridor where the same physics is rehearsed under slightly different local conditions. The companion interaction adds pressure to this engine by stirring the disk and compressing gas. It can raise star formation efficiency in some regions while stripping or heating gas in others. Tidal forces can also drive streaming motions along the arm, changing where shocks occur and where clouds assemble. The spiral's elegance seen in optical images is partly the visible trace of those gravitational perturbations. Inside the nebula, the paradox becomes a governing rule rather than a curiosity. Star formation requires cold, shielded gas, yet newborn stars rapidly unshield and heat their surroundings. The moment a massive star turns on, it begins dismantling the conditions that allowed it to form, an elegant self-limiting mechanism. The question is not whether feedback happens, but how long the cloud can resist it before the star wins. So the lifetime of a molecular cloud is limited, often only a few tens of millions of years. Clouds assemble, form stars, and are dispersed, even while the arm pattern persists. The arm is long-lived compared with any single cloud, so the same lane can host many generations of assembly and dispersal. What appears to be one continuous dark feature is really a succession of different clouds, each with its own brief history. The nebula is therefore a transient state in a larger flow. Gas enters the arm, becomes molecular, collapses into cores, then is returned to warmer phases by feedback. The transitions are not clean boundaries because phases overlap, and a single line of sight can contain cold clumps embedded in warm diffuse gas. In a multi-wavelength composite, those phases stack like transparent veils, each revealing a different piece of the same environment. From our distant vantage, telescopes see the integrated result as a sequence along the arm. CO and dust mark the fuel upstream, RH2 regions mark ignition downstream, and diffuse emission marks aftermath. When these traces are layered together, the arm reads like a storyboard of cause and consequence: compression, concealment, ignition, and erosion. The story is statistical, not deterministic, yet the pattern repeats often enough to be unmistakable. We keep descending until the story becomes less about one cloud and more about the galaxy's conveyor belt. The arm is a factory line, and each cluster is a brief product of unstable balance. The factory metaphor has limits, because nothing is perfectly repeatable, yet the pattern persists across thousands of light years. Each product also changes the factory, because feedback reshapes the next batch of incoming gas. Now the chapter turns toward motion, because newborn stars do not stay where they formed. Once they decouple from the gas, they follow orbits set by the galaxy's gravity. The gas can shock, cool, and change phase, but stars behave like collisionless test particles, carrying their birth signatures into the wider disk. Their chemistry and age become traces, like tags attached at formation, and carried outward by orbital flow. Galactic rotation carries young populations away from their birth sites. As they drift, their brightest massive members die, and the light of the population reddens with age. The change is visible in broad strokes: blue clusters near the arm's active edge, then softer, older light trailing behind. In time-lapse imagination, the arm would appear to sparkle, with new blue points igniting and then fading as they move downstream. This drift creates age gradients across spiral arms that observers can measure. The pattern links local physics to global dynamics, turning stellar populations into clocks. By comparing ultraviolet, optical and infrared maps, astronomers estimate how long it takes for gas to turn into stars and for feedback to disperse the remaining cloud. Those timescales are short compared with a galaxy's age, yet they set the pace of its ongoing renewal. We begin to zoom back out, keeping the nebula in mind as a unit of the larger disk. The next step is to track how these newborn stars migrate inward with the flow. The nebula's details remain essential, because every large-scale trend is built from countless local collapses, each shaped by the same paradox. The arm, seen from afar, is the sum of these hidden events, repeated until the pattern becomes a galaxy. Transition. Newborn stars don't stay put, and the galaxy does not pause for their formation. Gravity and rotation carry them onward, and we follow their aging light toward the inner galaxy. Newborn stars do not stay where the gas made them, even when their first light still clings to the cloud. They decouple from their natal cocoons as radiation, winds, and simple orbital motion pull them free. Then they enter the disk's orbit stream and begin aging as they drift away. In the first few million years, even a bound cluster is already changing shape, because gas expulsion weakens gravity and lets members leak outward. In M51, that drift is not subtle, because the spiral pattern is sharp enough to act like a ruler. The spiral looks like a sculpted wake in a river, and the stars are the foam that rides past it. A cluster that ignites inside a dense ridge can be carried downstream by galactic rotation, leaving the gas behind like a shoreline. The offset is small in absolute distance, yet enormous in meaning, because it turns geography into a timeline. Across M51, stellar populations sort themselves by environment, and the sorting has a physical logic that can be tested. Spiral arms concentrate the youngest, bluest stars because dense gas collapses there most often, and because the arm's gravity and shocks keep replenishing the raw material. Older, redder stars spread more smoothly because they have had time to mix, migrate, and blur their origins. Even the faintest background glow is a census. Billions of long-lived stars stacked in depth along our line of sight. This gradient is not a simple paint job laid over a spiral, and it does not come from one mechanism alone. It is the combined effect of where stars form and how orbits scramble them afterward, with each process leaving a different fingerprint. Gas shocks and cools inside arms, while stars pass through and keep going, carrying their ages like timestamps. When we map those timestamps, we are really mapping the competition between collapse, disruption, and orbital drift. The spiral arm is a traffic jam made of gravity, but the traffic is not made of cars. Gas streams into the arm, compresses, and loses energy through radiation, and that energy loss matters because it allows collapse. Cooling lets pressure drop, and when pressure drops, gravity can gather material into clumps that become star-forming cores. Stars, by contrast, are collisionless. Once born, they mostly ignore the arm's dense lanes and follow their own paths. The arm itself is also not a rigid object, and that subtlety is part of the mystery. In density wave language, the spiral is a pattern that rotates with its own speed, while gas and stars orbit at different speeds. Material flows through the pattern, lingers where it is slowed, and then exits, like water passing through a standing wave. That is why the arm can look steady in images, even while its ingredients are constantly replaced. On screen, the arms can be shown as luminous ribbons, but the real structure is layered and physically stratified. Dark dust lanes trace cold molecular clouds, where temperatures can fall to tens of Kelvin and molecules survive. Bright knots of ionized gas outline where ultraviolet light is carving cavities, and the edges of those cavities glow because electrons are recombining with protons. Behind that glare, older starlight forms a smoother glow, like embers under a flickering flame. In the arms, bright clusters mark recent ignition, and their edges often look ragged because stellar winds are already shredding the surrounding gas. Those winds are fast, and their momentum sculpts pillars and shells, leaving behind silhouettes that look almost architectural. Between arms, the light shifts toward longer wavelengths as massive stars vanish first, and the remaining population becomes dominated by longer-lived suns. The galaxy becomes an age map written by lifetimes, with colour acting as a shorthand for time. Colour, however, is not only age, and the narration can linger on that ambiguity. Dust reddens starlight by scattering blue photons more efficiently than red ones, and that can mimic an older population. Astronomers correct for this by combining bands, comparing ultraviolet to infrared, and using emission lines that reveal how much gas is being ionized. In M51, those corrections matter, because the same dust that hides young stars also marks where the densest star formation is happening. A massive star burns fast because its core runs hot and wasteful, forced into high-pressure fusion by its own weight. Higher core temperatures make fusion reactions extremely sensitive to conditions, so the star consumes fuel at a furious rate. Radiation pressure rises, convection churns, and the star becomes a turbulent engine rather than a quiet lamp. It may live only a few million years before its fuel balance collapses and its internal support fails. A sun-like star burns steadily because it can regulate itself, and that regulation is a profound piece of physics. When fusion speeds up, the core expands slightly and cools, and when fusion slows down, gravity compresses it and warms it again. That thermostat is why a solar mass star can shine for billions of years, quietly turning hydrogen into helium with patient efficiency. In the language of stellar structure, hydrostatic equilibrium and energy transport cooperate to keep the star stable for most of its life. Those different clocks create predictable patterns across a spiral, and the patterns are measurable rather than poetic. Ultraviolet and blue light hug the arms because only short-lived stars can keep them bright, and because those stars do not travel far before they fade or explode. Red and infrared light fill the disk because long-lived stars accumulate everywhere, building a background that thickens with time. Even without resolving individual stars, the integrated light carries the imprint of the initial mass function and the recent star formation history. Orbital mixing then blurs the original birth sites, and it does so in several ways at once. Differential rotation shears associations into streams, stretching clusters into arcs as inner orbits lap outer ones. Repeated passages through arms heat stellar orbits, increasing random motions and thickening the disk's stellar layer. Over time, what began as a compact nursery becomes a faint moving group, and then becomes indistinguishable from the general field. Even without dramatic encounters, the disk is a gentle blender, and its gentleness is deceptive. Small gravitational tugs from spiral structure can shift a star's guiding center inward or outward, a process sometimes called radial migration. This is not the same as heating, because a star can change its average radius without gaining much random motion. Over hundreds of millions of years, that migration can move stars across large fractions of the disk, softening gradients that were once sharp. M51 lets us see this record as a whole system, and that whole system view is rare in astronomy. In the Milky Way, we can measure individual stars precisely, but we struggle to see our own global structure because we sit inside the disk's dust and clutter. Our view is local, like trying to infer a forest's shape while standing under the canopy. In an external galaxy, we trade detail for a complete map, and the map reveals patterns we would otherwise miss. That trade has shaped astronomy for more than a century, and M51 sits inside that long arc. When Edwin Hubble resolved stars in nearby galaxies, the debate over island universes ended, and galaxies became laboratories rather than curiosities. Earlier still, Lord Ross's 1840s drawings of M51's spiral arms hinted that nebulae had structure, even before their true distances were known. Now, with space telescopes and sensitive detectors, we can read not just the stars but the gradients, offsets, and timing encoded across an entire disk. We can compare what we know locally with what we infer here, and the comparison is a test of universality. Nearby, we calibrate stellar ages, supernova yields, and remnant populations star by star, using parallax distances and detailed spectra. We also measure chemical abundances with high-resolution lines, separating oxygen from iron and tracing subtle isotopic clues. In M51, we test whether the same physics scales up across tens of thousands of light-years, where individual stars blur into populations. The life of a star is mostly quiet fusion, but the end is decisive, and the end changes everything around it. A star's mass sets its fate, and mass is set at birth by how clouds fragment under gravity, turbulence, and magnetic fields. Fragmentation is not random, because cooling and pressure determine a characteristic scale for collapse, while turbulence seeds density peaks that can become cores. The galaxy's future chemistry depends on that initial distribution, because different masses return different elements at different times. When we talk about mass-setting fate, we're also talking about a population rule that lets light become a diagnostic. The initial mass function describes how many low-mass stars form compared with high-mass stars, and it is surprisingly consistent across many environments. That consistency is important because it means we can connect light to mass, and mass to chemical enrichment, with fewer unknowns. Yet even small changes at the high-mass end would echo loudly, because massive stars dominate ultraviolet light and dominate feedback. Low and intermediate mass stars evolve slowly, and their slowness is part of their power. They spend most of their lives on the main sequence, then swell into red giants as hydrogen burning moves into a shell. Later, helium ignites in the core, and the star becomes a layered furnace with alternating shells of fusion. Convection dredges up processed material, and the star's atmosphere begins to carry the chemistry of its interior out into space. As these stars age, they shed envelopes through strong winds, and the winds are not gentle breezes. Pulsations and radiation pressure on dust grains help lift material away, creating expanding shells of gas that drift into the interstellar medium. The outflow can be slow by supernova standards, yet it is relentless, and over hundreds of thousands of years it can remove a large fraction of the star's mass. The exposed hot core then ionizes the lost gas, and the result is a planetary nebula, brief and luminous on galactic timescales despite the misleading name. Visually, planetary nebulae are like floating lanterns, and their symmetry can be startling. Their colours come from specific emission lines, with oxygen often glowing green-blue and hydrogen contributing red. Fine filaments reveal where fast winds from the hot core collide with earlier slower outflows, forming shocks and bright rims. In a galaxy-wide context, they are tiny points, but they mark a vast population of stars quietly returning processed material. When the envelope disperses, the core remains as a white dwarf, and its physics is both simple and strange. It is Earth-sized, supported by electron degeneracy pressure, meaning the electrons resist being squeezed into the same quantum states. Gravity is so intense that heavier elements sink, leaving a stratified atmosphere unless mixing disturbs it. The white dwarf has no new fuel source, so it cools for trillions of years, fading from white to red to black in theory. Most stars end this way, leaving quiet ash, and that quietness is deceptive in a chemical sense. White dwarfs store the history of their progenitors in their composition, usually carbon and oxygen, and their cooling rates can be used as clocks. Because the cooling is predictable, a population of white dwarfs reveals the time since star formation began in earnest. In old stellar populations, white dwarfs become a kind of archaeological layer, telling us how long the galaxy has been forming stars. Massive stars die differently because their cores build heavier elements in shells, and each shell has its own burning stage. Hydrogen fuses to helium, helium to carbon and oxygen, and then carbon, neon, oxygen, and silicon burning follow in rapid succession. The later stages happen faster and faster because the core loses energy through neutrinos, which escape almost without interaction. In the final days, the star becomes an onion of fusion, with the most advanced burning hidden deep inside. Fusion can make energy up to iron, but iron cannot power further burning, and that is the turning point. Iron has one of the highest binding energies per nucleon, so fusing it does not release energy, and splitting it costs energy. When the iron core grows too heavy, it collapses in seconds, and the collapse is a gravitational freefall halted only by nuclear forces. Electrons and protons are crushed into neutrons, and the core stiffens abruptly when nuclear density is reached. The collapse triggers a core collapse supernova, one of the most energetic events in a galaxy. A shockwave forms as the core rebounds, and a flood of neutrinos carries away most of the gravitational energy. Neutrinos rarely interact, yet in this extreme environment they can deposit enough energy to help revive the shock and complete the explosion. The outer layers are ejected at thousands of kilometers per second, and the explosion returns oxygen, silicon, and other alpha elements to the interstellar medium. For a moment, a single star can rival the brightness of an entire galaxy, and that fact still feels unreal. In a spiral arm, that flash is partly hidden by dust, but its aftermath is not. expanding debris ploughs into surrounding gas, lighting up filaments and arcs that can persist for tens of thousands of years. As the remnant expands, it sweeps up more mass than it ejected, and the shock slows while the shell brightens in radio and X-rays. Some massive cores halt as neutron stars, and the word halt hides a violent compression. They are city-sized objects where matter is squeezed beyond atomic density, with neutrons packed like a single giant nucleus. Their gravity is so strong that a teaspoon of neutron star material would weigh billions of tons on Earth. The surface is a crust of exotic nuclei, and beneath it the physics becomes uncertain, an active frontier rather than a settled textbook. If their magnetic beams sweep past us, we detect them as pulsars, and the regularity can be uncanny. A rotating neutron star can spin many times per second, and its lighthouse-like pulses can be timed with extreme precision. In that precision, astronomers find evidence of glitches, spin down, and the slow loss of rotational energy into surrounding space. The pulses also reveal the interstellar medium, because radio waves disperse as they cross ionized gas, turning timing into a probe of the galaxy's plasma. Other cores collapse further into stellar mass black holes, where the escape velocity exceeds the speed of light. We infer them when they accrete from companions and emit X-rays, or when their gravity shapes binary orbits in ways ordinary stars cannot. Accretion disks heat by friction and turbulence, and the innermost regions can reach millions of degrees, radiating strongly in high-energy bands. Each remnant is a fossil of past star formation, and each fossil hints at the mass spectrum of the stars that once burned. A third death pathway comes from white dwarfs in binary systems, where companionship becomes destiny. If a white dwarf gains enough mass from a partner or merges with another white dwarf, runaway carbon fusion can ignite under degenerate conditions. Degeneracy pressure does not soften as temperature rises, so the burning accelerates instead of stabilizing, and the star can detonate. This is a Type Ia supernova, and it can disrupt the star completely, leaving no compact remnant behind. Type Ia explosions have played a historic role in astronomy because they can be used as distance indicators. Their peak brightness is not perfectly uniform, but it correlates with how quickly they fade, allowing calibration. That relationship helped reveal the accelerating expansion of the universe. Yet here, in M51's disk, the same events are chemical factories. They are also time-delayed echoes of earlier star formation, because their progenitors must first evolve into white dwarfs. These different explosions matter because they seed different elements, and the timing of the seeding shapes the galaxy. Core collapse events enrich the galaxy in oxygen and silicon, building the raw material for rocks and for the chemistry life uses. Type Ia events add iron, changing cooling, altering stellar composition, and shifting how future generations of stars evolve. In a spiral disk, the mixture of these yields is not uniform, so chemistry becomes another kind of map. Nucleosynthesis is the hidden engine of galactic evolution, and it runs in stages that can be traced back to stellar interiors. Carbon is forged in helium burning through the triple alpha process, oxygen in later massive star stages, and silicon in advanced burning shells. Iron peaks in explosive burning and in Type Ia detonations, and the periodic table becomes a record of stellar interiors. Even rarer elements are made in extreme conditions, and their presence reminds us that not all enrichment comes from the same furnace. In a sense, the galaxy is a chemical ledger, and the metaphor holds surprisingly well. Every generation of stars withdraws hydrogen and helium, then deposits heavier elements back into the interstellar medium with interest. The balance sheet is written in spectral lines, where astronomers can measure metallicity by comparing the strengths of oxygen, nitrogen, and iron features. Those measurements depend on careful calibration, because temperature, density, and dust extinction can bias the line ratios if we are not cautious. Dust is part of the yield, not an afterthought, and it changes what we can see and what gas can do. Supernova ejecta can condense grains as the debris expands and cools, while winds from evolved stars add carbon-rich and silicate dust over long periods. Shocks can also destroy grains, so dust is constantly rebuilt and shattered, cycling between solid and gas. The same grain that blocks optical light can later become the surface where molecules assemble, turning obscuration into chemistry. On camera, dust is both veil and sculpture, and M51 makes that dual role easy to show. It darkens the starlight in sharp lanes, then glows in infrared when warmed by young stars. In multi-wavelength views, the same region can look empty in optical light, yet blaze in the infrared like a hidden furnace. When the view shifts again to radio, cold molecular gas appears, revealing that the darkest lanes are often the most physically crowded places. Enrichment changes the next generation's physics, and the change is not abstract or remote. More metals mean more cooling lines, allowing gas to radiate away energy and collapse into denser structures. More dust means better shielding and faster molecule formation, especially for molecular hydrogen, which forms efficiently on grain surfaces. With better shielding, ultraviolet radiation cannot penetrate as deeply, so cold cores survive longer and can reach higher densities. The galaxy's star formation efficiency is therefore tied to its chemical history, and the history is uneven across radius. Inner regions, enriched by repeated cycles, can cool quickly and form dense clouds, while outer regions may remain warmer and more diffuse. Even a modest metallicity difference can alter how easily a cloud fragments into cores, shifting the typical masses of stars that form. The disk becomes a laboratory where chemistry, cooling, and gravity negotiate the next outcome. The aftermath of explosions reshapes the gas, and it does so with geometry that can be visualized. Supernova remnants expand as shock waves that sweep up shells and heat interiors to millions of degrees, creating a hot plasma that shines in X-rays. Those X-rays trace cavities and bubbles, some isolated and some merged into superbubbles driven by clustered explosions. In dense regions, the shell can cool and become radiative, forming thin, bright filaments that outline the shock like a drawn circle. A remnant is not just a shell, it is a mixing engine with a long reach. The shock front stirs the surrounding medium, and instabilities wrinkle the interface between hot and cool gas. Rayleigh, Taylor fingers can push enriched ejecta outward, while turbulent eddies fold ambient gas inward, and the boundary becomes a braided contact zone. Over time, enriched material is diluted into the interstellar medium, though not instantly, and the galaxy's chemistry becomes patchy before it becomes smooth. Shocks do more than heat, and their extra work is invisible to the eye but not to physics. They accelerate cosmic rays, charged particles that can be boosted to near-light speeds by repeated crossings of the shock front. This diffusive shock acceleration turns a small fraction of explosion energy into a galaxy-wide population of fast particles. Cosmic rays diffuse through the disk and help ionize dense regions, and that ionization affects how gas couples to magnetic fields. Magnetic fields in turn influence collapse and fragmentation, especially where gas is only weakly ionized. Even a weak field can guide charged particles and shape the flow of ionized gas, and in dense clouds the field can provide support against gravity. Ambipolar diffusion allows neutral gas to drift past field lines, but the drift can be slow, and that delay changes collapse times. The result is a subtle negotiation between turbulence, magnetic tension, and self-gravity, and the outcome helps set the masses of new stars. Feedback can trigger star formation by compression, and the trigger can be dramatic when geometry cooperates. A shock can pile gas into a dense ridge that becomes unstable, forming new cores along the rim like beads on a string. In images, those rims can appear as arcs of H-alpha emission with dust just behind them, suggesting a moving front. The same feedback can also suppress star formation by dispersing clouds, shredding the very structures that might have collapsed. Whether triggering or suppression wins depends on timing and geometry, and the balance can change within a single region. If gas cools fast and stays confined, shells fragment and form stars before they dissipate. If turbulence and heating dominate, the cloud dissolves and the episode ends, leaving only a faint cavity. The question is always the same. Does the shock create a stable dense layer, or does it simply stir and thin the gas? On galactic scales, these local outcomes add up to regulation, a kind of self-control that keeps disks from burning out quickly. Star formation does not consume all gas at once, because feedback keeps most gas from collapsing efficiently, maintaining a low conversion rate per orbital time. Observationally, this appears as a long depletion time, often billions of years, even in galaxies rich with molecular gas. The spiral pattern organizes the cycle, but feedback sets the throttle, deciding how hard the engine can run. As we move inward, the throttle changes, and the environment becomes less forgiving in several coupled ways. Gas surface density rises, pressures increase, and orbital times shorten, so processes that take tens of millions of years in the outer disk can unfold faster near the center. The same feedback energy now interacts with denser surroundings and can create larger superbubbles, though they may be more confined. Shear also strengthens, and shear can stretch clouds until they fragment or disperse before they fully collapse. The inner disk also hosts older populations that dominate mass, and their presence is visible as a smooth, warm glow. Their distribution reflects billions of years of mixing and migration, and it provides the gravitational backbone of the disk. The arms still light up with blue fire, but the background grows redder and brighter, like a stage lit from behind. In that layered light, the galaxy's present is always superimposed on its deep past. This is why population gradients are expected in spirals, and why they are so useful for inference. Star formation sites are biased toward arms and dense rings, while stars themselves drift and spread through the disk's rotating frame. The galaxy's colour becomes a dynamical signature, telling us about motion as much as about age. If the gradient is too sharp, mixing has been weak or recent, and if it is too smooth, the disk has had time to stir itself thoroughly. We can measure these gradients with multi-wavelength maps, and each wavelength answers a different question about the same terrain. Ultraviolet traces the youngest massive stars, while H-alpha traces ionized regions around them where photons strip electrons from hydrogen. Infrared traces dust-heated star formation, and optical and near-infrared trace the older stellar mass that dominates the gravitational potential. Radio observations add the cold molecular component, tying the luminous outcome back to the raw reservoir. The power of these maps is in their alignment and their offsets, which can be subtle but consistent. In some regions, dust lanes sit slightly upstream of the brightest H-alpha knots, suggesting a sequence from compressed gas to newborn stars. Farther downstream, ultraviolet fades and optical light takes over, implying that the most massive stars have already died. The arm becomes a conveyor belt of phases: cold gas, embedded formation, exposed clusters, and then fading associations. We can also time the arm sequence using lifetimes, turning spatial offsets into clocks that work across thousands of light years. If the offset between gas ridges and young clusters is a few hundred light years, it implies a few million years of delay at typical orbital speeds. That delay matches the rapid evolution of massive stars and the short timescales of cloud collapse, especially once a dense core has formed. It also tells us that the arm's pattern speed and the disk's rotation are not mere kinematics but ingredients in the star formation recipe. This timing is one of the quiet triumphs of galactic astronomy, because it links scales that seem incompatible. It connects the physics of individual stars to the geometry of an entire spiral arm, connecting nuclear fusion to kiloparsec scale structure. It also raises a question that hangs over the whole disk. How many generations have passed through this same pattern, each leaving traces that slowly fade? When we watch the arm glow, are we seeing a transient episode, or a repeating rhythm that has persisted for billions of years? The same timing explains why supernova remnants cluster near arms, even when the arms themselves are moving patterns rather than fixed material. Massive stars do not live long enough to wander far before exploding, so their remnants mark where the most recent high-mass star formation occurred. In images, those remnants can appear as faint rings, filaments, or X-ray bright knots embedded in dusty lanes. Their distribution becomes a second tracer of the arm sequence, following the ultraviolet light with a short delay. Type Ia supernovae are less tied to arms because they require older systems, and their delay times are long. Their progenitors can take hundreds of millions to billions of years to explode, depending on binary evolution and mass transfer. They therefore occur in both arms and interarm regions, tracing older populations rather than fresh clusters. In a whole galaxy view, their more even placement is a reminder that not all violence is young. This mix of supernova types creates a chemical gradient, and the gradient is a memory of time as well as place. Inner regions, with repeated star formation and shorter mixing times, tend to reach higher metallicity, enriching the gas that forms new stars. Outer regions remain more pristine, with slower enrichment and fewer cycles of recycling. The gradient is also shaped by gas inflow and outflow, because metal-rich gas can be driven outward, while lower metallicity gas can be accreted inward. In spectra, that gradient appears as changing line ratios, and it can be mapped across the disk with careful modelling. Oxygen abundance often declines with radius, and nitrogen can show its own pattern because it is produced in different stellar channels. Temperature-sensitive lines and strong line calibrations each carry assumptions. so astronomers cross-check methods to avoid being fooled by excitation effects. These measurements are not just numbers, they are constraints on how gas flows, mixes, and returns. M51's interaction complicates and intensifies this picture, and the complication is visible in the spiral's dramatic clarity. Tidal forces from the companion drive streaming motions and compress gas, raising star formation in some zones and distorting the disk's kinematics. The arms can become more coherent, and the shocks stronger, because the gravitational perturbation organizes the disk into a grand design. The galaxy's ecology is being stirred from the outside, and the stirring amplifies the very gradients we are tracing. Historically, M51 became an icon because its spiral structure is so legible, and because it helped define what a grand designed spiral looks like. Early observers sketched its whorls, and later photographs revealed dust lanes and star-forming knots with increasing sharpness. In the 20th century, improved plates and larger telescopes turned the spiral from a curiosity into a benchmark, used to compare theories of spiral structure. Today we add ultraviolet, infrared, and X-ray layers, turning an aesthetic spiral into a physical narrative. The result is a feedback loop across scales, and it is not merely metaphorical. Tides strengthen spirals, spirals concentrate gas. Concentrated gas forms massive stars, and massive stars inject energy and metals. Those metals change cooling, and cooling changes fragmentation, and fragmentation changes the next generation's mass spectrum. The disk becomes a self-modifying machine, with each cycle changing the conditions for the next. Compact remnants are part of that machine's memory, and they persist long after the light fades. A population of neutron stars and black holes implies many past massive stars, even if the bright clusters have dispersed into the background. X-ray binaries and pulsars are signposts of that hidden history, blinking and flaring where the optical sky looks calm. In a galaxy like M51, each detected point source is a clue that the arm once hosted a massive star that has already vanished. Detection is itself a kind of translation, because the remnants speak in different wavelengths than ordinary stars. Pulsars announce themselves through radio pulses, while accreting black holes reveal hot inner disks that radiate in X-rays. In a distant galaxy, we often see them as points, but each point represents an extreme object and an ancient explosion. The fact that we can detect them at all is a triumph of instrumentation, because their signals must compete with diffuse emission and with the glare of the stellar disk. Hot gas is another memory, written not in points but in diffuse glow that fills cavities. Soft X-ray emission traces superbubbles and chimneys that vent energy into the halo, carving channels through the disk. The halo then acts as a reservoir, where gas can cool, condense, and later return, completing a circulation that links disk and outskirts. In this way, feedback is not only destructive, because it also redistributes material and sets up the conditions for future inflow. This circulation links star death to future star birth, and it makes the galaxy feel alive in a literal physical sense. Metals and dust return to the medium-enhanced cooling, while turbulence and heating delay collapse, and both effects matter simultaneously. The galaxy balances enrichment against disruption, and the balance shifts with radius, environment, and time. In M51, the balance is also being nudged by interaction, which changes where gas piles up and where it is stripped away. Closer to the center, the balance becomes more extreme and the margins narrow. Higher densities make cooling efficient, but stronger shear and tidal forces can tear clouds apart before they settle. The cycle tightens, the stakes rise, and the inner disk becomes a place where feedback and gravity compete at close range. Even the same supernova energy can have a different outcome here, because confinement is stronger and the surrounding medium is denser. We begin to sense a central influence, not yet seen directly but implied by motion and by asymmetry. Inflowing gas does not simply drift, because non-axis symmetric gravity can torque it, stealing angular momentum. Spiral arms and bars can remove that angular momentum, pushing enriched material inward along dust lanes and streaming flows. The physics is mechanical as much as thermal. Change the angular momentum and you change the radius where gas can remain in orbit. In images, these flows can be suggested by curved dust features that point toward the nucleus, like dark commas embedded in starlight. Gas piles up where orbits crowd, then slips inward in steps, like a river descending a staircase. Shocks along the lanes can compress and heat the gas, and the compressed gas can form stars even as it continues to migrate. The inward journey is slow compared with an explosion, Yet over cosmic time, it can reshape the entire central environment. The inward flow carries the products of stellar evolution, and it carries them mixed together rather than neatly sorted. Carbon-rich dust, oxygen-rich gas, and iron from old explosions ride the same streams as fresh hydrogen, passing through shocks and compressions along the way. Each passage can change the phase of the material, turning cold gas warm or shattering grains into smaller fragments that later regrow. The center becomes the meeting point of many lifetimes, where the disk's history converges. This is where the mystery shifts from local to systemic, and the question becomes sharper as the camera holds on the inner glow. If the inner cycle is faster and more violent, something is concentrating fuel and energy there, and the concentration is not accidental. What central engine sets the pace, and how does it respond when the disk delivers more material than it can quietly absorb? The spiral, once a beautiful pattern, now feels like a mechanism feeding a deeper process. Transition. Enriched gas does not just spread outward into space. It is torqued, funneled, and delivered inward, toward the region where gravity tightens its grip. We follow that flow toward the nucleus. The next chapter asks how inflow, pressure, and dynamics reshape star formation near the center, and it also asks what waits there to regulate everything. We have followed M51's arms as factories of light, chemistry, and feedback. Now we follow the fuel itself, because the center is not reached by drifting. The camera lingers on the grand design spiral, then slowly tilts into the disk plane, where motion becomes geometry, and geometry becomes fate. From above, the arms look like brushstrokes laid across starlight. From within the plane, they become corridors, and every corridor has rules. Gas does not choose a direction freely, because gravity and rotation have already written the traffic laws. Gravity is the sculptor, and rotation is the constraint that shapes everything else. In a spiral disk, matter wants to fall inward, but orbital motion keeps it suspended. Every parcel of gas is caught between two instincts: gravity pulling down the potential well, and angular momentum insisting on a wide, fast loop. That balance is not philosophical, it is measurable in kilometers per second. The disk is a clockwork of orbits, and the hands of that clock are the velocities we map. If we can read those velocities precisely, we can infer what mass must be present, even when it is dark. To understand that balance, astronomers start with a deceptively simple measurement: how fast the galaxy turns at different radii. The first clue is the rotation curve, the measured speed of gas and stars versus radius. It is built from Doppler shifts, where spectral lines slide minutely as material approaches or recedes along our line of sight. In practice, the measurement is a mosaic assembled from many traces. Optical lines like H-alpha follow ionized gas around star-forming regions, while carbon monoxide lines trace the colder molecular phase. Farther out, neutral hydrogen dominates, and its radio signal carries the rotation curve beyond the visible edge. The camera can show this as layered transparencies: blue knots of H-alpha, pale dust lanes, and then a faint radio disk that extends like a ghostly skirt. Each layer rotates, and each layer tells the same story in a different dialect. In the early days of galactic astronomy, the expectation seemed straightforward. If mass were concentrated in the bright disk, orbital speeds would drop outward. That is how the solar system behaves, where the sun holds most of the mass and the planets slow with distance. That expectation was rooted in Newtonian intuition and in what telescopes could see. For decades, the luminous disk looked like the galaxy, and the galaxy looked like its light. When observers first pushed to larger radii, they expected the curve to taper quietly into darkness. Instead, spiral galaxies often show flat rotation curves across wide radii. The outer disk moves too fast for the visible matter alone, so extra mass must dominate. The plot refuses to bend downward, and that refusal is a signature, one that has reshaped modern cosmology. A flat curve means the enclosed mass keeps rising with radius, long after the starlight fades. In plain terms, something heavy is still there, holding the outskirts in a fast orbit. The rotation curve becomes an argument written in motion, and it is difficult to ignore. The extra mass is the dark matter halo, extended and invisible, shaping the galaxy's gravitational potential. It does not glow, it does not absorb, and it does not trace the spiral arms like dust does. Yet its gravity is written into every orbit, like an unseen hand keeping the outer disk from loosening. We do not see the halo directly, but we see its consequences everywhere. The disk's thickness, its stability, and even the ease with which patterns grow depend on that background potential. The halo is the stage's weight-bearing frame, silent but structurally decisive. Historically, the surprise arrived in stages as radio astronomy matured. Neutral hydrogen, mapped through its 21-centimetre line, revealed rotation far beyond the optical edge. Those faint outer regions, nearly empty of starlight, still moved as if anchored by something massive. The 21-centimetre line itself is a subtle signal, born from a quantum flip in hydrogen's electron-proton alignment. It is rare for any one atom, yet abundant across a galaxy, and radio dishes learned to integrate patiently. With time, the outskirts emerged, and the flat curve became a recurring theme. That something is not a thin layer, but a vast, roughly spherical reservoir. A dark halo extends well beyond the bright spiral, often several times the visible radius. In simulations, such halos form early, providing the deep potential wells into which gas later settles and spins up. As the gas cools, it conserves angular momentum, and it cannot fall straight down the well. It spreads into a disk, thins, and begins to rotate, while the halo remains puffed and extended. The visual can shift to a time-lapse of structure forming, diffuse matter condensing, then flattening into a luminous whirl. A massive halo keeps the disk from flying apart at large radii, and it influences stability against global distortions. It also changes how strongly tides and patterns can torque gas. In other words, it sets the stiffness of the stage, even if it never takes a speaking role. In M51, the companions pull rides on top of the halo's gravity, amplifying non-circular motions. The spiral becomes not just a pattern of light, but a pattern of force. In the visuals, the arms brighten, then the scene overlays velocity arrows that subtly tilt away from perfect circles. Those arrows can be coloured by speed, so the viewer sees shear as a gradient, not a concept. Near the arms, the vectors bend as if the disk is being nudged sideways. The galaxy looks calm in photographs, yet in velocity space it is perpetually correcting itself. A rotation curve is more than a plot, because it is a map of where mass must be. From that map we infer where gravity is steep, where shear is strong, and where orbits crowd. The curve becomes a kind of fingerprint, telling us whether the disk is self-dominant or halo-dominated at each radius. It also tells us where differential rotation is harsh enough to stretch structures apart. Shear is not just a number, it is a force that shapes clouds, lanes, and rings. In a rotating disk, the difference between neighbouring orbits is a slow, relentless tug. But gravity alone does not guarantee inward travel, because angular momentum is the real gatekeeper. Gas in a circular orbit cannot simply fall inward without shedding that angular momentum. If it tried, it would speed up, overshoot, and settle back into another orbit, still circling, still held away from the centre. This is why the centre is hard to feed, even in a galaxy rich with gas. The barrier is not distance, but the need to change the orbit's character. To move inward is to change a conserved quantity, and nature demands a mechanism to do it. This is the angular momentum problem, and it is the central obstacle to feeding any nucleus. To move inward, gas must transfer angular momentum outward to something else. The phrase sounds abstract, but it is as physical as a spinning skater extending an arm to slow down. In a disk, that transfer can happen by exchanging angular momentum with other gas, with stars, or with the pattern itself. The key is asymmetry, because symmetry cancels forces. A perfectly round mass distribution cannot twist the gas overall, no matter how strong its gravity is. In a galaxy disk, the something else is often the disk itself via gravitational torques. Non-axis symmetric structures pull unevenly, creating a net twist on the gas. When the mass distribution is lopsided, even slightly, gravity gains a lever arm. Spiral arms, tidal tails, and ovals are all versions of that lever. They are density enhancements, and density enhancements create directional pulls. The camera can show the arm as a raised ridge in a gravitational landscape, with gas sliding along contours that are never perfectly circular. Spiral patterns exert torques, because they are not perfectly symmetric rings. Gas enters the spiral potential, is accelerated and decelerated, and its orbit becomes slightly elliptical. In the rotating frame, the spiral is a standing wave, and the gas is the moving medium forced to respond. The standing wave language matters, because the pattern can persist while individual gas parcels pass through it. The arm is not a permanent set of the same atoms, but a persistent gravitational instruction. That distinction, pattern versus material, helps explain why arms can be long-lived yet constantly renewed. Where the gas lags or leads the pattern, gravity does work on it, changing angular momentum. Over many orbits, small changes accumulate into large radial motion. The effect is gradual, like erosion, except the river here is time and the rock is orbit. You can picture it as a repeated bargain. Each pass through the arm trades a little angular momentum for a little inward progress. Then the gas coasts until the next encounter. The inward journey is therefore punctuated, not continuous, and the punctuation marks are the arms. The companion interaction strengthens this process by driving stronger spirals and tidal distortions. Tidal forces create streaming motions that are measurable as velocity departures from circular rotation. In M51, those departures are not theoretical. They appear as systematic wiggles in spectral maps and as skewed isovelocity contours. Historically, these streaming signatures became clearer as interferometers improved. Arrays of radio antennas began to resolve molecular gas into lanes and lanes into substructure. With resolution came a new kind of evidence. Not just that gas exists, but that it is being redirected. Inflow is therefore not a straight plunge, but a sequence of orbit adjustments. Gas moves inward in steps, guided by where torques are strongest and where dissipation can occur. The path resembles a spiral staircase, not an elevator shaft. The staircase metaphor is literal in phase space. The gas changes energy and angular momentum together, and those changes place it on a new orbit family. Each step is small, but the staircase can run for kiloparsecs, and the destination is measured in parsecs. Dissipation matters because gas is collisional, unlike stars. When gas streams intersect, shocks convert ordered motion into heat, and radiation then removes that energy. The shock is brief, but the consequences persist, because the gas has lost part of the energy that kept it on its previous orbit. In a shock, densities can jump by factors of several, and temperatures rise before cooling takes over. Cooling is efficient because atoms and molecules radiate in many lines, each one a tiny release valve. In a few thousand years, an eye blink on galactic timescales, the gas can cool and settle again. That energy loss lets the gas settle onto a new orbit with lower angular momentum. Stars cannot do this easily, because they mostly pass through each other without collisions. A stellar disk is a collection of near-miss trajectories, while a gas disk is a compressible fluid that can bruise and cool. This difference between gas and stars is why the galaxy can rearrange its fuel without rearranging its whole stellar disk. The fuel can be redirected while the older stars keep orbiting. Visually, the dust lanes shift and sharpen, while the underlying starlight remains smooth and steady. Now the documentary can linger on that contrast. Dark, narrow lanes etched across a golden disk. The lanes are not decoration, but the visible edge of a dynamical process. They are where the galaxy's invisible forces become visible through compression. We now map the hidden highways that carry gas inward, and the map is written in orbital families. In a rotating potential, not every orbit is allowed, and not every orbit is stable. The disk is not a free-for-all. It is a choreography constrained by resonances and by the galaxy's pattern speeds. Pattern speed is the rate at which the spiral's gravitational pattern rotates, and it need not match the material. That mismatch creates relative motion, and relative motion creates shocks. The viewer can see this as a subtle drift, gas overtaking the arm in one region, then being overtaken elsewhere. Resonances act like traffic circles in the disk, organizing where patterns exchange angular momentum with material. They are not places you can see directly, but they leave rings and lanes. When the narration speaks of a resonance, the visuals can show a faint circle, then a brightening ring of gas that seems to appear as if guided. These are not mystical boundaries, they are mathematical coincidences between frequencies. The orbital frequency, the epicyclic frequency, and the pattern speed align in special ratios. When they align, repeated forcing adds coherently, and the disk responds strongly. Corrotation is the radius where the spiral pattern speed matches the orbital speed of material. Near corrotation, gas can linger, and torques can change sign across that boundary. It is a subtle pivot point, where the spiral's gravitational push can switch from braking to boosting. Near that pivot, the flow can look hesitant, as if the disk is deciding which way to send its fuel. A slight change in pattern strength can shift the balance, and the same region can alternate between being a reservoir and being a conduit. That sensitivity is part of what makes galactic centers episodic. Inside corrotation, gas often orbits faster than the pattern and overtakes it. Outside corrotation, the pattern overtakes the gas and the relative flow reverses. This is why the same spiral can look like a conveyor belt in one region and like a headwind in another. This reversal matters because it changes where shocks form and where angular momentum is gained or lost. The same spiral can drive inflow at one radius and stall it at another. In a clean schematic, arrows point inward on one side of a boundary, then flatten into near-circular streaming beyond it. Lindblad resonances are other key boundaries, where epicyclic motions couple strongly to the pattern. They can trap orbits, crowd trajectories, and pile gas into rings. Epicycles are the small radial oscillations superimposed on circular motion, and resonances occur when those oscillations synchronize with the pattern's forcing. The epicycle picture can be visualized as a rosette traced by a slightly perturbed orbit. Most of the time, the rosette precesses and the pattern's pull averages out. At resonance, the timing locks, and the pull arrives at the same orbital phase again and again. An inner Lindblad resonance can create a nuclear ring, a dense belt where inflow slows and gas accumulates. A ring is not a decorative feature, but a dynamical consequence. It is a place where the galaxy's clockwork forces a pause, as if the highway narrows into a roundabout. In that roundabout, gas can circulate for many orbits, colliding with itself and becoming denser. The ring's surface density rises until gravity begins to win locally. Then the ring lights up with young clusters, and the pause becomes a burst. At these resonances, orbital families can switch from one orientation to another. Gas follows the stable family until shocks and dissipation let it jump to a new one. The transition can be abrupt in space, even if it is gradual in time, because the gas responds collectively like a fluid. Even a small change in orbital orientation can matter, because it changes where streams intersect. Intersections are where shocks form, and shocks are where energy is lost. The ring, the lane, and the inflow are therefore different faces of the same underlying geometry. In barred galaxies, this is often described as X1 and X2 orbit families. M51 is not dominated by a strong bar, but weaker oval distortions can play similar roles. Even a mild oval can create a preferred axis, and that preference is enough to torque gas over many rotations. Even without a classic bar, the combined spiral and tidal field can create bar-like torques in the inner disk. The result can be offset dust lanes and inward streaming along them. In the imagery, these lanes appear as dark brush strokes, slightly displaced from the stellar ridge, hinting at compression and flow. Resonances therefore regulate inflow by creating bottlenecks and reservoirs. They can also ignite star formation by raising surface density above instability thresholds. The same structure that slows the gas can also squeeze it, and squeezing is the first step toward collapse. When gas piles up into a ring, it is compressed, shielded, and made molecular more efficiently. The ring becomes a staging area, where fuel waits and then bursts into stars. Shielding matters because molecules like H2 survive where dust blocks destructive ultraviolet photons, turning diffuse material into a colder, denser phase. In molecular gas, cooling becomes even more effective, because molecules radiate rotational and vibrational lines. Carbon monoxide, though not the most abundant molecule, becomes a convenient beacon. Observers use it as a proxy, translating line brightness into mass with careful, imperfect calibrations. This is where the narrative tightens, because inflow is both a delivery system and a trigger. The same torques that move gas inward can also create the conditions for rapid collapse. The galaxy is not simply transporting fuel, it is changing the fuel's state as it travels. We can trace these flows through dust lanes and shocks, because dust marks where gas is densest and most compressed. A dust lane is often the visible edge of a shock front. Against the glow of older stars, dust becomes a silhouette, revealing where the interstellar medium has thickened into a narrow ridge. In high-resolution images, the lanes look braided, with filaments splitting and rejoining. Some segments are sharply defined, while others dissolve into mottled patches. That texture is the signature of turbulence and cloud substructure, written in extinction. In spiral arms, dust lanes sit on the upstream side of star formation. In the inner disk, dust lanes can become long, straight features that point toward the center. Those straight lanes are especially telling, because they suggest strong shear and organized inflow in the rotating frame. Shocks form where gas streams converge in the rotating frame. Density jumps, temperatures rise briefly, and molecules can be both formed and destroyed depending on shielding. The chemistry is fast by astronomical standards, with cooling lines from carbon, oxygen, and CO radiating energy away on short timescales. After the shock, cooling is fast, so the gas becomes dense and cold again, but now on a different orbit. The lane is therefore a signpost of redirection, not just obscuration. It is the mark of a decision already made. Angular momentum has been traded, and the gas cannot return unchanged. Velocity maps confirm this picture by showing streaming motions along the lanes. The gas does not follow perfect circles, and those deviations are the fingerprints of torques. In a moment of visual clarity, the documentary can overlay observed velocity fields, where contours bend and pinch near the dust ridges. Those bends are not noise, they are coherent patterns repeated from arm to arm. The ISO velocity lines can even appear to kink at the shock, like a river bending around a rock. The viewer is watching gravity's handwriting, traced by gas that cannot lie about its motion. Inflow rates are not constant, and they can vary with pattern strength and interaction phase. M51's companion can modulate inflow by changing spiral amplitude over time. A close passage can strengthen the spiral, then the pattern relaxes, and the inflow responds like a tide that rises and falls. This variability introduces a kind of memory into the centre. Gas that arrives now may have been launched inward hundreds of millions of years earlier. The nucleus is therefore fed by the galaxy's past, and the present spiral pattern is partly an echo of earlier encounters. As we move inward, orbital times shorten, and the same physical processes accelerate. A few tens of millions of years in the outer disk becomes a few million years near the centre. The camera's pace can mirror that acceleration, with cuts tightening and the rotation seeming to quicken. The environment also changes in ways that matter for star formation. Gas surface density rises, pressure rises, and turbulence becomes harder to dissipate. The interstellar medium becomes less like a quiet fog and more like a crowded weather system, full of collisions, eddies, and abrupt fronts. In that crowded weather, clouds are not isolated objects with clean edges. They are transient over densities, constantly stirred and reassembled. The question becomes not whether clouds form, but whether they can remain coherent long enough to collapse. The inner few hundred parsecs of many spirals resemble a central molecular zone, like the Milky Way zone. It is a region of high density, high velocity dispersion, and complex chemistry. In infrared and millimeter light, it glows with molecular lines that trace temperature, density, and shock history. The Milky Way's central molecular zone taught astronomers that density alone is not destiny. There, the gas is abundant, yet the star formation rate is lower than naive scaling laws would predict. That mismatch forced a rethinking of what efficient means in a hostile gravitational environment. In the Milky Way's central molecular zone, gas is abundant, but star formation is oddly inefficient for its density. Turbulence, shear, and magnetic support can delay collapse. That inefficiency is one of the great puzzles of nearby galactic ecology, because the raw material appears ready, yet the conversion into stars remains throttled. M51's inner region likely faces similar tensions, even if its exact numbers differ. High density should favour star formation, yet strong tides and turbulence can keep clouds marginal. The question is not whether gravity is present, but whether gravity can win locally before the environment tears structures apart. A central molecular zone is not one cloud, but a crowded ensemble of clouds and streams. Collisions are more frequent and shocks are more common, raising the baseline pressure. In such a zone, even the quiet state is dynamic, with filaments feeding clumps and clumps being shredded into filaments. High turbulence broadens spectral lines and increases internal support, raising the effective gene's mass. That can shift fragmentation toward fewer, more massive cores in extreme conditions. In plain terms, turbulence can make it harder for small pieces to collapse, nudging the system toward larger, rarer birth sites. Shear is stronger near the centre, because orbital speed changes rapidly with radius. Shear can stretch clouds, preventing them from collapsing unless they become very dense. A cloud that might collapse in the outer disk can be pulled into an arc here, its self-gravity fighting against differential rotation. Tidal forces also intensify, and they can unbind loosely held structures. A cloud must be compact enough to survive the differential pull of the central potential. This is the roch-like logic of galactic centers, where only the densest condensations remain coherent for long. Magnetic fields strengthen toward the center in many galaxies, partly because gas density and turbulence amplify them. Stronger fields can guide flows and add support against gravity. Field lines can also channel shocks, shaping dust lanes into straighter, sharper features, and influencing how quickly gas can slip across them. Cosmic ray densities and radiation fields also rise, because star formation and supernovae are more concentrated. This changes ionization, heating, and the chemistry that sets cooling rates. A higher ionization fraction couples gas more strongly to magnetic fields, altering how turbulence decays and how clouds fragment. The interstellar medium becomes an environment under pressure, with warmer molecular gas and more pervasive high-energy photons. Dust temperatures rise, and shielding becomes a sharper boundary. In the visuals, the palette shifts from optical blues to infrared reds, where warm dust and dense gas reveal the center's hidden weather. These changes alter the initial conditions of star formation. Cores may start warmer, more turbulent, and more magnetized, which changes accretion histories and feedback coupling. The stars that form can still resemble familiar ones, yet the path to forming them is more contested and more violent. The question becomes whether inflow builds a steady central star-forming zone or triggers a starburst. The difference is partly a threshold problem, set by surface density and stability. A center can hover near a tipping point for long periods, then cross it quickly when inflow strengthens or a bottleneck releases. A starburst happens when gas accumulates faster than it can be consumed or expelled, pushing the region into runaway formation. Feedback then rises sharply, and the system reacts. The burst is not merely bright, it is mechanically disruptive, injecting momentum and heat into the surrounding medium. A steadier mode happens when inflow, star formation, and feedback balance each other. The center then forms stars continuously, but at a regulated efficiency. Regulation does not mean calm, because the balance can be maintained through constant stirring, with turbulence acting as the thermostat. Thresholds can be framed through tomb stability, where rotation and pressure compete with self-gravity. High surface density lowers stability, while high velocity dispersion raises it. The tumor parameter is a compact way to express a complex reality, translating rotation curves and turbulence into a single diagnostic. In the inner disk, both terms increase, so the outcome is not obvious. Gas can be dense enough to collapse, yet turbulent enough to resist, until a trigger tips the balance. That trigger can be as large as a tidal pulse, or as local as a collision between two streams in a crowded orbit. Triggers can include a change in torque strength, a resonance-driven pileup, or a cloud collision in a crowded orbit family. Interaction with NGC 5195 can supply all three. The companion does not need to touch the center directly, because it can reshape the spiral's force field, and the disk transmits that change inward. When a burst ignites, feedback becomes a central actor rather than a local one. Radiation pressure, winds, and supernovae can pressurize the region and drive outflows. The center becomes a furnace with vents, and the vents open where the surrounding medium offers the least resistance. Outflows can vent along the minor axis if the disk offers a low-density escape route. They can also stall if the surrounding medium is dense, trapping energy and raising turbulence. A stalled outflow is not a failure. It is a way of storing energy in the gas, keeping it hot and restless. This creates a feedback loop that can self-regulate star formation by keeping gas stirred and warm. It can also blow gas outward, temporarily starving the center of fuel. The same process that limits star formation can, paradoxically, preserve gas for later, delaying collapse until conditions change again. Yet feedback can also compress gas in shells and rings, triggering secondary star formation. The center can therefore flicker between suppression and ignition, depending on geometry and timing. In a sequence of images, expanding bubbles intersect dense lanes, and new clusters appear like sparks along the edges. The inflow itself is not immune to feedback. Hot gas and turbulence can change how effectively torques couple to cold clouds, altering the rate at which angular momentum is removed. If cold clouds are shredded into a more diffuse phase, they may respond differently to the spiral's gravitational lever arm. We now connect the large-scale gravity map to the small-scale star formation story. The same torques that move gas inward also decide where it becomes molecular and where it fragments. The galaxy's dynamics and its chemistry are not separate chapters, because compression, Shielding and cooling are all consequences of orbit. Dust lanes show where shocks compress gas, resonances show where it piles up, and feedback shows where it is dispersed. The center is the sum of these competing instructions. One force gathers, another scatters, and the observed structure is the compromise written in gas and dust. As gas approaches the inner tens of parsecs, the potential becomes more dominated by the bulge and the nucleus. Orbits become rounder in some zones and more chaotic in others. The bulge adds a smoother, deeper gravitational field, while the nucleus introduces a steep inner rise that changes precession rates and resonance locations. Even subtle changes in precession matter because they shift where orbit families align and where they intersect. A resonance that sits at one radius in a quiet epoch can drift when the mass distribution changes. The disk is therefore not a static machine, but a machine that slowly retunes itself. The last barrier is again angular momentum, now at much smaller scales. Even if gas reaches the central few hundred parsecs, it still must shed orders of magnitude more angular momentum. The difference between a 100 parsec orbit and a 1 parsec orbit is not a small adjustment, but a vast reduction in rotational support. Galaxies solve this with nested mechanisms, a cascade of torques and dissipation. Large-scale spirals feed inner spirals, ovals feed rings, and rings feed still smaller structures. Each stage works where it can, because the physics that dominates at a kiloparsec does not automatically dominate at 10 parsecs. This is sometimes called the bars within bars idea, but the broader point is a hierarchy of non-axis symmetries. Each stage hands gas inward to the next stage. The handoff is rarely clean because star formation, feedback and resonances can intercept the flow at every level. At each handoff, resonances can both help and hinder. They can trap gas into rings that form stars, consuming fuel before it reaches the nucleus. A ring can be a reservoir, but it can also be a sink, converting inflow into starlight and supernovae before the gas advances. This is the central mystery in practical form. Does most inflowing matter turn into stars in rings and clusters, or does some fraction reach the very center? The question is not only about supply, but about timing. How long the gas can remain cold and coherent while the environment grows harsher. If it reaches the final few light years, the rules change again. The gravitational influence of a supermassive black hole becomes unavoidable, and orbital speeds climb steeply. The sphere of influence is small compared with the galaxy, yet it is decisive because the potential becomes sharply centralized. Near that sphere of influence, the potential is close to Keplerian, and small perturbations can send gas into tight eccentric orbits. Collisions and shocks can then become extreme. In a tight orbit, even a modest change in angular momentum can produce a dramatic change in pericenter distance, bringing streams into violent intersection. Accretion onto a black hole requires still more angular momentum loss, now through viscosity, magnetic stresses, and instabilities in a compact disk. The inflow becomes a different kind of flow. What was once a galactic-scale river becomes a disk-scale whirlpool, where microscopic processes matter because the scales are so small. But the black hole is not the only possible sink. Dense gas can fragment into stars even very near the center, creating a nuclear star cluster or a compact starburst. In such regions, star formation and accretion can compete directly for the same inflowing material, each altering the other's conditions. Whether gas forms stars or feeds, the black hole depends on density, temperature, turbulence, and tidal shear. It also depends on how feedback from the nucleus alters the surrounding medium. A slight increase in nuclear activity can heat or ionize gas, changing its ability to cool and settle into a thin, accreting disk. A quiet nucleus can allow gas to accumulate until a burst ignites. An active nucleus can heat or expel gas, reducing star formation while still accreting intermittently. The center can therefore alternate between phases, not because the laws change, but because the balance between cooling, inflow, and feedback drifts. In M51, the nucleus is not a blazing quasar, but it shows signs of activity. That suggests low-level accretion that can still matter for regulation and for the inner gas state. Even a modest active nucleus can drive jets or winds that sculpt the circumnuclear medium, leaving subtle cavities and excited emission lines. We are now close enough that every earlier concept converges. Dark matter set the outer rotation, spirals and tides applied torques, resonances organized traffic, and shocks marked the lanes. The story has been narrowing, from a halo spanning hundreds of thousands of light years to a region where a few parsecs decide what happens next. The inflow has built a denser inner environment, where star formation can become intense, inefficient, or episodic. The centre is not a destination, but a decision point. What looks like a simple inward drift is actually a sequence of gates, each one asking whether the gas will collapse, stall, or continue. Transition. The inflow converges on the nucleus, and the last stable orbits begin to narrow. The visuals tighten to the inner disk, where dust lanes curve into smaller arcs, and the light becomes more concentrated, as if the galaxy is drawing breath. We cross into the inner parsecs, where the black hole's gravity competes with every other force. The next chapter follows what happens when the centre starts answering back. In that answering, through radiation, winds, and the reshaping of nearby gas, the galaxy reveals whether its heart is merely fed or truly awakened. We cross the last crowded lanes of the inner disk, where orbits tighten and time seems to speed up. The glow ahead is not just brighter starlight, because the spectrum itself changes, harder, hotter, and more compact. It is the signature of a deeper gravitational well, one that steepens the rules of motion and concentrates the consequences of every encounter. Even the background light feels different here, because it is built from countless overlapping sources packed into a smaller angle. A galaxy center is defined by concentration, but also by contrast, because it gathers mass while breaking symmetry. The bulge rises above the disk as a dense, older stellar component, rounder in shape and richer in long-lived low-mass stars. Those stars are often metal-rich, because earlier generations lived and died, seeding the region with heavier elements. In many spirals, that bulge formed early, when the universe was more chaotic and mergers were common. The nuclear region sits inside it, where gravity steepens sharply and random motions increase, and where the galaxy's smooth glow breaks into knots, dust lanes, and sudden points of light. Here, stars are packed into a smaller volume, so encounters are closer and velocities are higher. The typical separation between stars shrinks, and the speed distribution widens, because the gravitational potential changes rapidly with radius. In the disk's outskirts, a star can orbit for eons with little disturbance, but the nucleus offers no such quiet. Gas surface density climbs, pressures rise, and shocks become routine, especially where inflowing streams collide and lose orbital energy. The center is where the galaxy's energy budget and its future become hardest to separate, because the same gas can either form stars or feed something darker. Visually, the spiral arms that looked like graceful brushstrokes now feel like converging currents, as if the whole disk leans inward. Dust filaments curl inward like smoke, tracing magnetic fields and shear, and the background glow becomes granular with unresolved stars. In optical light, the nucleus may look modest, even slightly obscured, because dust is most effective where gas piles up. In infrared, that same region can brighten dramatically, revealing warm grains heated by intense radiation and by collisions in dense clouds. In radio maps, the dust becomes almost irrelevant, and the center can snap into focus as a compact source embedded in diffuse emission. Astronomers do not simply point a telescope and declare a nucleus, because galaxies stack their structures along our line of sight. They disentangle overlapping light sources that sit on top of each other, separating what is physically central from what merely appears central. They separate smooth bulge starlight from compact nuclear emission using resolution, spectra, and careful modelling. That modelling is not cosmetic. It is a quantitative attempt to assign each photon to a plausible origin. A bright pixel can be a cluster, a dust window, or an active core, and the difference is the whole story. Historically, this problem shaped the development of galactic astronomy, because early instruments blurred the very scales that matter. 19th century observers could sketch bright cores, but they could not measure what powered them, and the debate lingered for decades. In the early 20th century, spectra began to sort nebulae from stars, and later they revealed that some galaxy centers contained unusually excited gas. Only with spectroscopy, and later with space-based imaging that escaped atmospheric blur, did nuclei become testable physical objects. Even now, the nucleus is often smaller than a single pixel in a wide-field image, so inference becomes the main instrument. Starlight has absorption features from stellar atmospheres and a predictable continuum shape, because stars are thermal emitters with well-understood photospheres. Their spectra carry fingerprints like the calcium H and K lines, the magnesium triplet, and the Balmer series, each shaped by temperature and gravity. When many stars blend together, those features broaden, but their ratios still reveal age and chemical enrichment. Nuclear activity adds non-stellar components, including hot dust, high ionization lines, and hard X-rays that require electrons at extreme energies. The trick is to decompose the mix without mistaking a dense star cluster for a black hole, or confusing a dusty starburst for an accretion-powered source. One method is spectral synthesis, where astronomers fit the observed light with combinations of stellar populations of different ages and metallicities. Another is imaging decomposition, where a smooth bulge profile is subtracted to reveal compact residuals at the center. The uncertainties matter because a small error in the bulge model can create a false extra nucleus. In a galaxy like M51, where dust lanes thread the core, extinction can also reshape the apparent brightness profile, hiding structure in one band and revealing it in another. Even the point spread function, the way a telescope smears light, must be treated like a physical ingredient, not an afterthought. In M51, the central region is small on the sky, yet it is physically decisive. It is measured in parsecs, but it can influence kiloparsecs, because gravity and feedback do not respect the scale of our images. The question tightens to a single possibility, posed again and again in modern astrophysics. Is there a supermassive black hole at the core? Supermassive black holes span a wide mass range, from millions to billions of suns, and their masses correlate with their host bulges. That correlation, sharpened into relations with stellar velocity dispersion and bulge mass, emerged through decades of dynamical measurements. It hints that galaxies and black holes co-evolve rather than grow independently, trading influence through gas supply and feedback. They are not made by piling up ordinary matter into a dense star, because pressure and nuclear burning cannot stabilize such a configuration. They are compact objects defined by gravity so strong that light cannot escape, and by space-time curvature that dominates every nearby orbit. The event horizon is not a surface you can stand on, and it is not a material boundary. It is a boundary in space-time where escape requires moving faster than light, which no signal can do. Outside it, physics still follows known laws, but the margin for stability collapses as tidal forces and orbital speeds rise. Even so, the horizon itself is deceptively simple in concept, an invisible radius set by mass and by the geometry of space-time. If you could watch a clock near the horizon, its ticking would appear to slow, a relativistic effect that turns gravity into a distortion of time. For a non-rotating black hole, that radius is the Schwarzschild radius, proportional to mass. For a rotating black hole, the horizon shrinks and an ergosphere appears, where space-time is dragged around with the spin. Rotation matters because it can change how efficiently accretion converts mass into radiation, and it can help power jets through magnetic coupling. These are subtle effects, yet they can decide whether a nucleus whispers or flares. Spin is also a historical record because it can be built by long-term feeding or scrambled by mergers. We do not see the horizon directly in most galaxies, especially at M51's distance, because the angular size is unimaginably small. Even the Event Horizon Telescope, which imaged horizons in much nearer systems, relies on Earth-sized baselines and millimeter wavelengths. For M51, we infer the black hole by its influence on nearby matter, and by the energetic signatures that cannot be explained by stars alone. Gravity leaves a measurable pattern in orbital speeds, and in the energies released by infalling gas, and those patterns persist even when the central engine is faint. The cleanest evidence comes from dynamics, because motion responds directly to mass. If stars or gas orbit a compact mass, their velocities rise as distance shrinks, following a Kepler-like trend when one object dominates. When the implied mass is too large and too concentrated to be a star cluster, a black hole becomes the simplest explanation. The key is concentration, because a diffuse mass distribution can mimic high mass without requiring a horizon. Astronomers therefore ask a strict question: how much mass fits inside how small a radius? In practice, observers map Doppler shifts across the nucleus, searching for rapid rotation or broad line widths. They use integral field spectroscopy to capture a spectrum at each point, then reconstruct velocity fields like weather maps. They estimate enclosed mass from velocity and radius, then compare it to the light present, translating brightness into stellar mass with population models. If mass exceeds what luminous stars can supply, something dark dominates, and the argument becomes difficult to evade. The strongest cases show a steep central rise that cannot be smoothed away by any plausible star distribution. Yet even this method has pitfalls, because gas is not always a clean tracer of gravity. Gas can be pushed by pressure gradients, stirred by turbulence, or accelerated by outflows, and those non-gravitational forces can broaden lines. Stars are more faithful, but harder to measure, because their absorption features are faint in a dusty nucleus. The best cases combine multiple traces and multiple wavelengths, building a consistent mass estimate from independent angles. When those angles agree, the center's hidden mass stops being a hypothesis and becomes a constraint. But dynamics is only half the case, because the center also radiates in ways stars struggle to mimic. Some nuclei emit hard X-rays, compact radio cores, and emission lines requiring intense ionization, including species that need photons far beyond what ordinary stellar populations produce. Line diagnostics compare ratios of forbidden and permitted transitions, separating star-forming regions from harder, accretion-like spectra. Those signatures point to accretion, not fusion, because they require extremely hot electrons and very compact emission regions. The nucleus becomes a laboratory, where energy conversion is gravitational rather than nuclear. Accretion is the engine that turns a black hole from silent to spectacular, and it is one of nature's most efficient power sources. A black hole does not shine by itself, because nothing escapes from within the horizon. It shines when matter falls in and converts gravitational potential energy into heat and radiation, releasing energy as it spirals down the potential well. In plain terms, falling inward is like descending a steep mountain, and the lost height becomes heat. The closer the gas gets, the steeper that mountain becomes, and the more expensive each remaining step is in energy. Gas cannot drop straight in, because it carries angular momentum from the galaxy's inflow, inherited from the disk's rotation. It spirals inward and forms an accretion disk, a flattened flow where neighboring rings orbit at different speeds. Differential rotation creates shear, and shear creates dissipation, because adjacent layers rub and exchange energy. The disk is not a rigid object, it is a dynamic, turbulent conveyor belt for mass and angular momentum. In high-resolution simulations, it looks less like a smooth record and more like boiling weather, with eddies, waves, and magnetic knots. The word friction is a shorthand, but the real driver is turbulence and magnetic stress within ionized gas. Magnetized plasma develops instabilities that tangle fields and transfer angular momentum outward, most famously through the magnetorotational instability. As angular momentum moves out, mass moves in, and the disk can continue feeding the center rather than stalling. This is a subtle point, yet it explains how accretion can proceed despite the disk's natural tendency to conserve rotation. Without that transport, gas would simply orbit forever, bright perhaps, but unfed at the core. As gas drifts inward, it falls deeper into the gravitational potential and heats up, and the heating rate rises sharply toward the center. The inner disk can reach temperatures that radiate in ultraviolet and X-rays, while outer regions glow in optical and infrared. Above the disk, a hot corona of tenuous electrons can scatter photons to higher energies, adding a hard X-ray tail. The energy released per unit mass can exceed nuclear fusion efficiency, because gravity near a black hole is so steep, and because the last stable orbits sit so close to the horizon. In effect, the disk extracts energy from orbital motion and then radiates it away. This is why quasars can outshine entire galaxies, even though the black hole itself occupies a region smaller than a solar system. A luminous accretion disk can convert a significant fraction of rest mass into radiation, approaching 10% or more for spinning black holes. A galaxy of stars must burn fuel slowly, because fusion is limited by stellar structure and by long lifetimes. An accreting black hole can radiate intensely while consuming far less mass, turning a trickle of gas into a lighthouse. The light can also vary rapidly, implying that the emitting region is compact, because large regions cannot change coherently in short times. In the most extreme cases, the luminosity approaches the Eddington limit, where radiation pressure balances gravity for ionized gas. That limit is not a hard wall, but it sets a scale for how bright steady accretion can be without blowing itself apart. It also ties luminosity to mass, which is why bright quasars imply massive black holes even before dynamics are measured. The universe's brightest nuclei therefore reveal not just energy, but also hidden mass. When we see a quasar at great distance, we're also seeing an early rapid chapter of black hole growth. Yet the same physics allows quietness, and that quietness can be deceptive. A supermassive black hole can be present and still look dim, even when it sits at the dynamical centre of a galaxy. The difference is not the black hole's existence, because the horizon does not turn off. The difference is the supply rate, the disk structure, and how efficiently the flow radiates, which depend on temperature, density, and magnetic configuration. In other words, the engine is there, but the fuel line may be thin, intermittent, or turbulent. When the nucleus is starved, accretion can become hot and tenuous, and the disk can puff up into a thick, faint flow. The gas may not cool into a thin, bright disk, because radiative cooling becomes inefficient when the density is low. It can form a radiatively inefficient flow, where energy stays in the plasma and is carried inward or expelled rather than radiated. In plain language, the gas stays too hot and too thin to shine brightly, even as it falls. Some of what would have become light instead becomes motion, feeding weak winds or a compact jet. Low luminosity activity has a distinct fingerprint, and it often requires patience to detect. X-rays may be weak but hard, indicating very hot electrons and compact emission. Radio emission may show a compact core, sometimes with a tiny jet, even when optical light looks ordinary. Optical lines may indicate mild ionization, with ratios that hint at a harder spectrum than young stars provide. The nucleus can flicker without becoming a beacon, and that flicker can be the only clue that accretion continues. The question is not only whether it shines, but how its spectrum betrays the conditions of the flow. Multi-wavelength diagnostics are essential because dust and stars confuse the optical view, especially in a spiral like M51. Infrared can reveal warm dust heated by a central source, even when the source is hidden behind thick lanes. X-rays can pierce columns of gas that block visible light, tracing the hottest regions near the disk and the corona above it. Ultraviolet, when it escapes, can highlight compact hot regions, but it is easily absorbed and irradiated by dust. Each band is a different slice through the same engine, and none is complete on its own. Radio observations add another clue because radio waves pass through dust almost unimpeded. Some black holes launch jets, narrow beams of plasma guided by magnetic fields, and those jets can persist even when the radiative output is modest. Even weak jets can produce compact radio emission and carve channels in surrounding gas, leaving linear features or small lobes. In some systems, the radio core is the most stable signpost of the central engine because it changes less with obscuration. When a jet is present, it also provides a direction, an axis that can organize the surrounding chaos. The classic unification picture introduces a dusty torus, a thick ring of obscuring material around the nucleus. Orientation then changes what we see, even if the engine is similar, because the torus blocks some lines of sight and opens others. In some directions, broad emission lines are hidden and only narrow lines escape, produced farther out where velocities are lower. This idea emerged as astronomers compared different classes of active galaxies and realized that geometry could mimic diversity. It was a reminder that classification can be a trick of perspective, not a fundamental difference in physics. The torus is not necessarily a smooth donut, and modern observations suggest it is clumpy and dynamic. Clouds can move, collide, and evaporate, changing obscuration over time and causing nuclei to change look in some cases. Dust grains also have temperature limits, so the inner edge of the torus sits where dust sublimates, creating a sharp boundary set by luminosity. Even this boundary can be measured through infrared reverberation, where dust responds to changing light with a time delay. In images, the torus is rarely seen directly, but its presence is written into spectra and timing. M51's nucleus is not a quasar, yet it is not inert, and that in-between state is scientifically rich. Evidence points to a modest active galactic nucleus, embedded in a busy nuclear environment where star formation and inflow compete. The center is therefore a furnace of light and a test of regulation, because small engines can still reshape their surroundings. The mystery is not whether the nucleus matters, but how it matters when it is not blazing. A faint core forces us to measure carefully, because it cannot overwhelm the scene and simplify the accounting. Around the black hole, the environment becomes extreme in several linked ways, and each one feeds the next. Tidal forces rise steeply with decreasing radius, so clouds must be denser to remain bound and avoid being torn apart. Velocity dispersion increases, so collisions and shocks become more energetic, converting bulk motion into heat and turbulence. The gravitational potential also changes rapidly, so shear becomes stronger, and differential rotation can stretch clouds into filaments. In molecular maps, those filaments can appear as twisted lanes, as if the gas is being combed by invisible hands. Radiation fields intensify from both young stars and any accretion-powered source, and the spectrum hardens as you approach the center. Ionization and heating alter chemistry and cooling, changing how gas fragments and how quickly it can shed energy. Molecules can be dissociated, dust can be heated, and the balance between atomic and molecular phases can shift. The same gas that formed stars easily in the arms may struggle to collapse here, because the conditions punish coherence. It raises a quiet question. How close can a cloud approach the center before the center rewrites what a cloud can be? This is the nuclear star formation problem in miniature, and it is a recurring theme across spiral galaxies. High density suggests rapid star birth, because gravity has more material to work with. Yet strong shear and turbulence can delay collapse, because they inject kinetic energy and prevent clouds from settling. The center can contain abundant molecular gas and still form stars inefficiently, as the Milky Way's central zone demonstrates with its dense clouds and surprisingly low star formation rate. Even when stars do form, the initial conditions can bias their masses and lifetimes, altering the feedback they return. One way to frame the problem is with stability criteria, like the Tumri parameter, which compares self-gravity to shear and pressure. In the arms, gas can cross the threshold and fragment into bound clumps. Near the center, the same surface density may not be enough, because the epicyclic frequency is higher and the shear is stronger. The result is a region that looks fuel-rich but behaves fuel-poor, a paradox that forces astronomers to think beyond simple density arguments. It also suggests that more gas is not a guarantee, because the rules of collapse change with the orbit. Dense star clusters can also dominate the nuclear light, and they can be extraordinarily compact. A compact starburst can mimic some signatures of an active nucleus, especially in infrared, because dust heated by massive stars glows warmly. Supernova remnants can also produce radio emission, and hot gas can emit soft X-rays, complicating the picture. Astronomers separate them by looking for hard X-rays, compact radio cores, rapid variability, and line ratios that require non-stellar ionization. The goal is not to dismiss star formation, but to measure how much of the energy budget belongs to each engine. The nuclear region is therefore a crowded competition for the same fuel, and the competition is not polite. Gas can fragment into stars, locking mass into long-lived objects and returning some through winds and supernovae. Or it can remain diffuse and feed the black hole, releasing energy quickly and potentially expelling what remains. Feedback from either channel can change the outcome for the other, because both stars and accretion inject heat, momentum, and radiation. In the center, cause and effect can swap places, because today's outflow becomes tomorrow's missing fuel. Accretion does not only radiate, and this is where the nucleus becomes more than a light source. It can drive winds and jets that push back on the galaxy, coupling tiny scales to large ones. This is feedback, and it is the mechanism that turns a central engine into a regulator, rather than a passive sink. In the language of galaxy evolution, feedback is how a galaxy prevents itself from turning all its gas into stars at once. It is also how a small region can matter, even when it is faint. Jets deposit energy mechanically, drilling through gas and inflating cavities that can be traced in radio and X-ray images. Winds carry momentum and heat, sweeping up shells and shocking the surrounding medium, and their speeds can reach hundreds or thousands of kilometers per second. Even a low-luminosity nucleus can have an outsized mechanical effect if it couples efficiently, because mechanical power does not require dazzling brightness. The question becomes whether the outflow hits dense gas or escapes through a porous medium. In one case, it stirs the inner disk like a spoon, and in the other it vents like a chimney. Feedback can suppress star formation by heating gas and preventing it from cooling, which keeps it from fragmenting into bound clouds. It can expel gas from the nuclear region, lowering surface density and breaking the inflow chain that feeds both stars and the black hole. It can also compress gas in shocks and shells, triggering star formation in dense ridges where pressure rises suddenly. The same physics can therefore both quench and ignite, depending on how energy is delivered and where it lands. When we see a bright rim around a cavity, we are seeing a boundary where pressure has become architecture. The same action can therefore both quench and ignite, depending on geometry and timing, and the nucleus rarely acts in a symmetric way. A wind that vents along a low-density path may leave the disk intact, like steam escaping through a crack. A wind that ploughs into dense lanes may overpressurize clouds and change their fragmentation, possibly creating brief starbursts along the edges of cavities. In images, this can appear as arcs of young stars or as bright rims around evacuated regions. The asymmetry itself is a clue, because it reveals where the gas is thick enough to resist. In M51, interaction-driven inflow from the companion can modulate the fuel supply, and that modulation is part of the Whirlpool's identity. The spiral pattern and tidal torques deliver gas inward in episodes, not as a steady stream, because gravitational forcing varies with orbital phase. Gas can lose angular momentum as it shocks along dust lanes, then drift inward until another barrier or resonance slows it again. That sets up a nucleus that can alternate between quiet accumulation and sudden feeding, like a reservoir that fills, then spills. The visual spiral, so calm from afar, is also a map of torque and loss. Time variability becomes a central theme because accretion responds to supply and to internal instabilities, and the response can be non-linear. A small change in inflow rate can flip the disk state, changing radiative efficiency and the balance between disk, corona, and jet. The nucleus can brighten, then fade on timescales far shorter than the galaxy's age and sometimes shorter than a human lifetime. That variability is a reminder that a galaxy's center is not a static monument, but an active machine. If we could watch for long enough, we might see the center breathe, slowly, irregularly, but unmistakably. Astronomers look for evidence of past activity, even when the present looks calm, because the environment can remember what the nucleus has done. Fossil bubbles in hot gas can mark earlier outbursts that inflated cavities, leaving low-density regions surrounded by brighter rims. Ionization echoes can persist when light from a past flare travels outward and excites distant clouds, creating glowing structures that outlive the flare itself. In some galaxies, these echoes appear as cones or filaments, like searchlights frozen into the interstellar medium. The center may be quiet today, yet its past can still be written in the gas like a faint afterimage. These fossils matter because they reveal duty cycle, the fraction of time a black hole spends in active states. A black hole may spend most of its time quiet, then grow in bursts, because fueling is intermittent and feedback can self-limit. Over cosmic time, those bursts can still build most of the black hole's mass, even if each episode is brief. This is one reason the universe's quasar era, billions of years ago, still matters for understanding quiet nuclei today. It also reframes a dim nucleus as a phase, not a verdict. The center is therefore not a final destination, and it is not merely a drain. It is a switchyard where inflow, star formation, and feedback exchange control, and where small changes can redirect the entire system. The same torques that fed the nucleus can be weakened if feedback heats the inner disk and changes its response, raising pressure and thickening the gas layer. In that case, the inflow lanes that once delivered fuel can become less effective, and the nucleus can starve itself by pushing too hard. Regulation in this sense is not a single lever, but a set of competing tendencies that can cancel or amplify. This is where the earlier question returns with force, because structure and feeding are linked. Are M51's arms a long-lived rhythm, or a transient pattern amplified by interaction? The answer changes how often the nucleus is fed, and how strongly it can regulate the disk, because the arms are not just decoration. They are gravitational patterns that organize gas, set shock locations, and determine how efficiently angular momentum is removed. When we admire the spiral, we're also looking at a machine for moving matter inward. If the spiral is sustained, inflow can be persistent, building a steady nuclear reservoir that keeps the center supplied. If the spiral is episodic, inflow arrives in pulses tied to tidal phases, and the nucleus may alternate between dormancy and activity. Either way, the nucleus becomes a recorder of the galaxy's recent dynamical history, because it responds to what the disk delivers. In this sense, the core is like a seismograph, registering the galaxy's gravitational weather. The record is imperfect, but it is real, and it is written in gas density, line widths, and faint high-energy light. At the smallest scales, the black hole's sphere of influence sets the final boundary conditions, and it is defined by where the black hole's gravity overtakes the star's collective pull. Orbits become nearly Keplerian. and small angular momentum changes produce large changes in pericenter. So trajectories become sensitive, streams intersect, shocks intensify, and the accretion flow becomes responsive to tiny perturbations, including turbulence and passing stars. The result is a region where order and chaos coexist, and where the next brightening can be seeded by a minor disturbance. Even a single cloud's misstep can matter, because the potential is so steep. At the same time, the nuclear star cluster and bulge provide a dense background of stars, each one a moving source of gravity and gas. Stellar winds add gas, supernovae inject turbulence, and stellar gravity perturbs gas orbits, stirring the flow and changing collision rates. The black hole does not act alone, even when it dominates the potential at the very center. It acts inside a living, crowded ecosystem, where stellar evolution and accretion physics overlap. The center is therefore not one object, but a negotiation among many, played out in motion and heat. There is also a chemical story embedded in this environment, because the center is enriched by generations of stellar death. Metals, elements heavier than helium, cool gas efficiently, and they also build dust grains that absorb and re-radiate light. That cooling can help clouds collapse, yet the same dust can hide the process from optical view, forcing astronomers to rely on infrared and radio tracers. In the nucleus, even the composition of the gas becomes part of the feedback loop, because enrichment changes how the next cycle behaves. The center, in a quiet way, becomes a historian of its own recycling. The climax is the realization that the nucleus is both consumer and governor, and that the two roles cannot be separated. It consumes inflowing matter, turning some into radiation and some into outflows, but it also returns energy that reshapes the supply. The galaxy feeds the center, and the center answers back, sometimes gently through heating, sometimes sharply through shocks. The answer is not a single event, but a pattern of responses that accumulate over time. What looks like a stable spiral can hide a long argument between gravity and pressure. That answer propagates outward through pressure, turbulence, and changes in cooling, and it can travel along the same lanes that once brought fuel inward. It can alter how efficiently clouds collapse in the inner disk, changing the balance between bound clumps and diffuse gas. Over long times, it can shift the balance between star formation in the arms and the retention of gas for future cycles, subtly rewriting the galaxy's trajectory. The arms may still look serene, but their future can be decided by the core. The most distant stars may never approach the nucleus, yet they can still inherit its consequences. We step back and see the loop as one system, because the boundaries we draw are conveniences rather than physical walls. Spiral structure concentrates gas and drives inflow, organizing shocks along dust lanes and building reservoirs near the center. Star formation and stellar death enrich and stir the medium, adding turbulence and radiation that reshape the gas. The black hole, quiet or luminous, modulates the conditions that decide what happens next, and it does so through both light and motion. The loop is not perfectly closed, but it is tight enough to matter, and it is written into the galaxy's shape. In this wider view, the nucleus is no longer just a point of mystery, but a node in a network of cause and effect. The disk sets the supply, the center sets the response, and the response alters the disk's next move. An ongoing negotiation. The whirlpool's beauty, seen from afar, becomes a visible trace of invisible exchanges of energy and angular momentum. It invites a question that lingers. How many of the galaxy's grandest patterns are actually consequences of its smallest engine? Transition. The heart of the whirlpool is not merely a point of arrival. It is a regulator whose moods can rewrite the galaxy's future. Transition. We pull away from the nucleus to reframe the entire whirlpool as a coupled engine. Arms, interstellar medium, star formation, and the black hole close into one feedback loop, each part shaping the others across scales. The final chapter will test that loop against the whole galaxy, using the disk as a record of what the center has done. It will ask what M51 is becoming and what its center implies for spirals like the Milky Way. The journey inward ends by changing how we read the beauty at the edges, because the edges are never truly separate from the core. We pull back from the nucleus and let the whole whirlpool reassemble until arms and core lock into a single rotating design. The central question returns in one frame, sharpened by scale. What processes shape a spiral galaxy from arms to core, And what do they reveal about our own? The answer is not a single monster or a single cradle, and it is not confined to one dramatic event. It is an ecosystem that cycles matter through phases and regulates itself through feedback across many orbits. Gravity provides the deep potential and the orbital clock, setting speeds and shear that never stop. Gas and dust provide the fuel, the chemistry, and the memory of past generations, stored in metals, molecules, and grains. Start with the arms, because the arms are where the cycle becomes visible in light and shadow. Spiral structure organizes orbits and crowds gas into shocks and lanes, like traffic piling into a curve. Compression turns diffuse hydrogen into molecular clouds, and dust shielding allows cooling to proceed by radiating energy away. Carbon monoxide becomes a tracer for that cold phase, while the true mass hides in molecular hydrogen. Collapse follows when turbulence and magnetic support lose the local argument against self-gravity, and the cloud fragments. Nebulae ignite, and star formation writes time into the arm as a sequence of colours. Massive stars carve H2 regions, their ultraviolet photons stripping electrons from hydrogen and making the gas glow. Their winds push into their birth clouds, sculpting pillars and cavities that look delicate but are violently overpressured. Supernovae inject heat, turbulence, and cosmic rays, and they seed the gas with metals forged in stellar cores. Enrichment increases cooling efficiency, and dust grows in outflows and dense clouds, and the next generation forms under altered conditions. Feedback does not end the cycle. It redirects it, sometimes gently, sometimes with a shock front. Hot bubbles vent into thicker halos or stall and pressurize the disk depending on local density and gravity. Shells can trigger secondary collapse along their rims, while turbulence can delay it for tens of millions of years. The result is low-efficiency star formation that still dominates the galaxy's visible light, because the brightest stars are also the shortest lived. Redistribution closes the loop, and it does so with the quiet certainty of orbital mechanics. Differential rotation shears clusters into streams and spreads metals across the disk, turning local fireworks into global chemistry. Radial migration moves stars away from their birth radii, blurring the record in starlight and complicating any attempt to read history from position alone. Gas flows respond faster, and shocks and torques keep rearranging the fuel, especially where the spiral pattern compresses it. This is the galaxy as a cycle, not a snapshot, and the timescales overlap like gears. Inflow along arms feeds inner reservoirs, and star formation consumes part of that inflow as it passes. Stellar death returns part of the mass, enriched and heated, to the interstellar medium through winds and explosions. Cooling and shielding rebuild cold clouds, and collapse begins again, even while older stars drift onward. Transition. The journey inward only makes sense when we see the return flow outward. The center matters because it changes the boundary conditions for everything else, even when it looks calm. Central gravity organizes orbit families and sets resonance locations that act as gates, where patterns can trap or redirect gas. Those gates create rings, bottlenecks, and sudden pileups that can trigger bursts when density crosses a threshold. The inner disk becomes a switchyard where small changes in torque produce large changes in supply, and where shear can both stir gas and tear clouds apart. Nuclear star formation is one response to that supply, and it can be surprisingly compact. Dense gas can form clusters packed into tens of parsecs, where radiation pressure and winds quickly become dominant forces. Their winds and supernovae can drive outflows that look like chimneys in X-rays and filaments in optical emission. Those outflows can heat and thicken the inner disk, weakening future inflow by raising pressure and turbulence. A starburst can therefore be both a consumption event and a self-limiting break, leaving behind a changed medium. The black hole is the other response, and it is the most compact regulator in the entire system. Even a low luminosity active nucleus can drive mechanical feedback through jets or winds, converting accretion energy into motion. That feedback can excavate cavities, shock dense lanes, and change the phase balance of the inner gas from cold to warm and hot. The center can answer back without becoming a quasar, and the disk still feels the reply. The key lesson is coupling across scales, because the galaxy is one machine with many levers. Kiloparsec spirals deliver gas inward through torques and dissipation, bleeding angular momentum away in shocks. Parsecs decide whether that gas becomes stars, becomes an accretion flow, or is expelled by feedback. The outcome propagates outward through pressure, turbulence, and altered cooling, changing how the next arm passage behaves and how bright it becomes. M51 makes this coupling easier to read because we see it from outside with geometry laid open. We can measure offsets between dust lanes and young clusters and time star formation along a pattern as it rotates. We can map streaming motions and infer where angular momentum is being traded using line profiles that reveal hidden flows. We can compare the nucleus to the disk without the confusion of living inside it, where distance and extinction distort every map. Now compare the Whirlpool to the Milky Way, because the mirror is the point and the discomfort is useful. Both are spiral disks embedded in dark matter halos, with ongoing star formation and multiphase gas layered by temperature. Both host central black holes, and both show inner regions where dense gas does not guarantee efficient star formation. Both rely on feedback from massive stars to keep the gas from collapsing too quickly, and to keep the disk from burning out. The differences teach us what environment changes, and they explain why two spirals can feel so unlike. M51's arms are unusually prominent, and the companion has amplified them through tides that stretch and compress the disk. That interaction likely boosts inflow, sharpens shocks, and modulates nuclear fueling in episodes rather than steadily. The Milky Way lacks such a close companion today, so its spiral pattern may be weaker, more transient, or driven by different instabilities. Even our central bar, still debated in detail, may play a larger role in organising inner gas than M51's present structure. From inside the Milky Way, our view is biased by dust and distance ambiguities, and by the simple fact that we sit in the plane. We infer structure through velocities and models, and we argue about bar strength, arm number, and pattern speeds because multiple solutions fit partial data. From outside M51, geometry is simpler, and the disk becomes a clean laboratory for spiral triggering and gas response. External viewing shows us what a grand design spiral looks like when you can see the whole machine, and when you can align traces without guessing distances. This comparison reframes the opening hook, and it adds a quiet warning about interpretation. Falling inward along glowing arms does not end at a single revelation, because no single scale owns the story. It ends at a control point that can be quiet for long periods, then flare briefly when supplying conditions align. The center is not always violent, but it is always consequential, because it sits where flows converge. Zoom out again, because M51 is one galaxy in a universe of spirals, and the pattern repeats with variations. Spiral disks are common outcomes when gas cools inside rotating dark matter halos, a framework that emerged as simulations improved in the late 20th century. Angular momentum preserves extended disks, while instabilities and interactions generate patterns that redistribute it without erasing it. Over cosmic time, accretion from the cosmic web replenishes gas and merges threatened disks while also building bulges. The history is written in structure: thin disks, thick disks, and central concentrations that remember past heating. Feedback is the universal counterweight, and it is why galaxies do not convert all their gas into stars at once. Stellar feedback regulates star formation in most disks, preventing rapid gas exhaustion by stirring and heating the interstellar medium. Black hole feedback becomes decisive in massive galaxies, and can quench star formation by heating or expelling gas from central reservoirs. The balance between inflow, cooling, and feedback shapes the galaxy population we observe, from blue star formers to red-quenched systems. M51 sits in the middle of that story, close enough for detail, distant enough for perspective, and famous enough to anchor a century of images. It shows how interactions can sculpt spirals without destroying the disk outright, producing order from disturbance. It shows how star formation can be organized by patterns that are not made of fixed material, but of moving density enhancements. It shows how a modest nucleus can still participate in regulation, even when it does not dominate the galaxy's light. Open questions remain sharp in 2026, and they are sharpened by how much we can already measure. Are M51 spirals long-lived density waves, or transient features continually refreshed by tides and swing amplification? How does star formation efficiency change in extreme inner environments, where shear and turbulence rise, and where cloud lifetimes may shorten? What triggers black hole feeding in a mostly quiet nucleus, and what sets its duty cycle across millions of years? When we see a faint nucleus today, are we catching a lull, or a long equilibrium state? Magnetic fields and cosmic rays remain missing pieces because they are hard to measure and easy to underestimate in simple models. Fields can guide shocks, support clouds, and alter angular momentum transport by coupling gas to larger-scale flows. Cosmic rays can heat and ionize gas, changing chemistry and coupling to fields through pressure and streaming. Together, they may help explain why dense gas sometimes refuses to form stars, even when gravity seems to have the advantage. The observational future is built on synthesis across wavelengths, because each band reveals a different phase of the same cycle. Radio arrays will map cold gas and magnetic structure with finer resolution and sensitivity, tracing CO, HI, and polarized emission across the arms. Infrared telescopes will separate embedded star formation from older stellar light through dust emission and spectral features, revealing hidden clusters still wrapped in their cocoons. X-ray observatories will trace hot plasma, supernova remnants, and faint accretion signatures near the core, where mechanical feedback leaves its fingerprints. Time domain surveys will matter as much as images, because regulation is a verb, not a noun. Variability in X-rays and radio can reveal accretion state changes and jet activity, even when the nucleus is modest. Proper motion and spectral mapping can refine pattern speeds and resonance locations, tightening the link between theory and observed offsets. Long baselines in time will turn the galaxy from a photograph into a process, and they will test whether patterns persist. Multi-messenger astronomy may also enter the spiral galaxy story, not as spectacle, but as accounting. Neutrinos and gravitational waves trace compact object populations and merger histories, linking stellar evolution to rare but consequential events. Those events seed heavy elements and can inject energy into surrounding gas, leaving chemical and dynamical traces. Even nearby spirals become part of a broader network of cosmic signals, where different messengers confirm the same physical narrative. Transition. The closer we look, the more the Whirlpool becomes a rulebook for other galaxies. Return to the full Whirlpool one last time, and the mystery resolves into balance, not into simplicity. Beauty emerges from gravity's relentless rules, and from matter's ability to cool, collapse, and ignite under the right conditions. Creation and destruction are not opposing chapters, they are alternating steps in one engine, paced by orbits and feedback. The arms shine because the cycle keeps restarting, and the center matters because it can change the cycle's timing. What really happens inside is not hidden behind dust forever, because physics leaves multiple signatures. It is written in offsets, velocities, spectra, and faint high-energy light, each one a clue with a timescale attached. It is written in how gas becomes stars, and how stars remake the gas through radiation, winds, and supernova shocks. It is written in how a black hole can influence a disk without dominating its light, acting more like a valve than a beacon. The journey inward ends by sending us outward with sharper questions, and with a more disciplined sense of cause and effect. If M51 can be read as a coupled machine, then the Milky Way can be read the same way, even from our embedded viewpoint. Our own origins are tied to the same cycle of inflow, collapse, feedback, and enrichment, repeated over billions of years. Understanding one spiral in detail is a step toward understanding the universe of spirals and toward understanding why any disk remains luminous. We drift back into deep space, and the Whirlpool becomes a single rotating island again, suspended in a darker sea. Its center is no longer just a destination, but a regulator embedded in a living disk, connected to the arms by invisible flows. The final image is not an ending, it is a reminder. Galaxies live by cycling matter, and their hearts help decide how long the light can last. We began with a pinwheel of light, then learned to read it as an archive, where every photon carries 23 million years of history. Across the disk, gravity and dark matter set the clockwork, while spiral patterns gather gas into dust lanes, cool it into molecules, and spark clusters that briefly outshine their birth clouds. Those stars then unmake their own cradles, through radiation, winds, supernova shocks, cosmic rays, and magnetic fields, returning enriched material to the interstellar sea, and keeping star formation inefficient but relentless. The arms themselves are not painted on, they are motion made visible, and M51's companion keeps touching the canvas. Tidal forces from NGC 5195 amplify the spiral contrast, twist velocity fields into streaming wiggles, and torque gas so it can shed angular momentum, step inward, and sometimes stall in rings and resonances. In that inward drift, we saw the galaxy become denser, hotter, and more obscured, until infrared and radio replaced starlight as our guide. Near the centre, the story tightens into a competition for the same fuel, between nuclear star formation and a black hole that may spend long eras quiet, then flare in brief, regulating outbursts. Even when the nucleus looks modest today, the disk can preserve its fingerprints: cavities, ionization echoes, disturbed gas, and altered star formation efficiencies, like scars that only multi-wavelength vision can read. And yet, some of the most important answers remain productively unfinished because M51 is still moving. Are its arms a long-lived density wave rhythm, or transient features repeatedly refreshed by tides and swing amplification? And does the difference control how often gas reaches the centre? What exactly sets the black hole's duty cycle? How turbulence, shear, magnetic tension, and cosmic rays either choke inflow or suddenly let it cascade inward? The Whirlpool teaches us that a spiral galaxy is not a static photograph, but a living engine whose most beautiful structures are the surface patterns of deeper forces. So, at the centre, is the Whirlpool a nursery or a predator, a forge of suns or a hungry black hole? It is both, and more importantly, it is a regulator where gravity delivers fuel, stars and shocks contest it, and the black hole answers in quiet lulls or sudden shaping breaths. The warning we felt in the arms was not that the centre destroys the galaxy, but that nothing here is ever simply stable. The spiral's elegance is a temporary agreement between competing processes, renewed orbit by orbit, and rewritten each time the companion tugs, the gas cools, the stars ignite, and the nucleus responds. When you look at the Whirlpool, you're not seeing a design, you're seeing a conversation between matter and motion, between creation and disruption, between the disk's wide patience and the centre's concentrated power. And if M51 is a mirror, then the Milky Way is not a finished home, but a changing system, where our own night sky is the visible edge of invisible physics. Keep watching the Whirlpool in every wavelength and across time, because the next decisive clue may be a faint echo, an offset in a spiral arm, a ripple in gas, or a sudden flicker from the dark.